All right, I have clicked the start streaming button. Let me wait for it to show up. There it is. And I can share that. Let me copy that link. Hello, viewers. N6MTS, Smitty Halibut here. I'm going to type this into chat so that Paul can send it out to his social medias as he feels fit. I will do the same on mine. Mark Smith, N6MTS, Smitty Halibut here. I am live with Paul Braun. Braun? Brown? How do you pronounce it?
Either.
Braun, however you pronounce that. WD9GCO. Did I get that right? Okay, I'm terrible with call signs. Paul is a good friend of mine. He's he's a viewer or listener of the Ham Radio Workbench podcast, but he's also an anchor of Amateur Radio Newsline. So you might hear his bassy, dulcet tones and recognize them. That's where you recognize them from. He and I have been chatting a lot about Open Headset Interconnect Standard and what it takes to make adapters for that. And he decided he would like to make his own user-side adapter for his particular headset, which is a Dave Clark headset. Is that right?
Well, it is. It's Dave Clark OEM. These Motorola sold them. They may have sold them to the military, but they're made by David Clark. But they also have been used a lot. I've seen around racetracks.
Yeah. So very good, noise blocking, big, long, high quality microphone element on a long boom and whatnot, and really good headsets. But they have this unique connector. It's not unique to Dave Clark. I think it's an aircraft aviation connector, and it's this. It looks like no, that's not even the one I'm thinking of. Yeah, so it's like this little short, stubby quarter-inch, but not quarter-inch, and it's a 4-pin. It's this weird, unique connector. I can't remember. Do you have a part number for it, by chance, Paul?
You know what? Actually, there's one. Well, yeah. It's made by Nexus.
Okay.
And it's a U93A/U, and there's an M part number on it, which I assume means military. So, but it's made by Nexus. It's a U93A/U.
Are you on Mastodon?
I am.
There you are. I was looking for you by Paul, and it wasn't showing up. And I are doing a live stream. See, the reason I'm having to do all of this after we've started the stream is because YouTube won't actually give me the URL to the live stream until I've started the live stream, which is kind of annoying, but here we are.
Yeah.
So y'all get to watch me tweet this out and send it out over Mastodon and whatever else. Do live stream getting started with KiCAD. Come join us and throw peanuts. Okay. And publish. Okay. So I've gotten that out on mine. Let's actually, what window is that going to, yep, I thought that was going to come up with the wrong one. Of course it does. So let's go over here. I'm going to put this in the Ham Radio Workbench rag chew. Paul. Yep. WD9. There you are. And I are doing a live stream getting started with KiCAD. Sorry for anybody who's coming back and watching this not live. You might want to skip ahead a minute or two. I will make these talking head windows shrink when we actually get to the technology here. Come watch us. Keep in mind that your browser is on the stream right now.
And I'm posting here on the Ham Radio Workbench Facebook page.
Rock and roll.
All right.
Okay.
There we go.
There we go. Okay. So that is done. I think we've shared it out with all the socials. I'm going to go ahead and scroll it. Oh, come on, if I can grab it. Scroll that over to the right, make us smaller, make your desktop bigger. And let's talk about what we are going to do today. All right, so the purpose of this video is to do a quick, I don't know how quick, but to do kind of a getting started with KiCAD. First thing I'm going to talk about is it pronounced KiCAD or KiCAD? This is right up there with, is it pronounced GIF or GIF? And I am not going to get into the religious debate. I don't have a strong opinion. I call it KiCAD, but because that's the way that I read it the first time I saw it written on screen. Plenty of other people call it KiCAD. I think mostly Europeans call it KiCAD, and given that it was developed in Europe, if I remember correctly, I think Germany, KiCAD is probably more correct, but I still call it KiCAD. I don't care. Paul has been watching other videos and said that he's heard it pronounced KiCAD, so that's the way he started pronouncing it. I told him before this video started that we are both going to pronounce it different ways, and that's okay, and we should probably do that just to drive the pedants mad who are who have a strong opinion one way or the other.
I'm perfectly fine with driving them crazy.
Yeah, so my point is that it doesn't matter what it's called. We all know what we're talking about, so pronounce it however the heck you want to pronounce it.
By the way, it's GIF.
It's, well, see, I pronounce it GIF, right? Because, like, if your argument is because it's graphic, it's a hard G graphical.
Yes.
Then why isn't it JPHEG? Because photographic is not F. It is a PH. Why is it not JPHEG? Yeah, exactly.
Whatever.
So
you're wrong. It's GIF.
It's whichever.
Let's just move on.
It is whichever. Neither is right nor wrong. It does not matter one way or the other. Anyway, religious debates behind us. So he's also using KiCAD 7, which I have not transitioned to yet. I'm still using 6 because I was in the middle of a product development cycle when 7 came out, and I'm like, I'm going to hold off on that.
And not come on, where's your sense of adventure?
My sense of adventure is back there with my dwindling savings account because I only just started selling a product that might actually be able to pay me a salary. So
yeah, there you go.
Yeah. So anyway, we may run into some differences between 6 and 7 that I'm not aware of, so we might get caught up with that a little bit. Okay. But from the most part, we're going to do a relatively simple project. He has this metal box. Can you show that? Okay. He has this metal box, and if you can see right here, I don't know how well this is going to come out on a live stream when all of the resolutions get shrunk and expanded and whatever else. But there is a little slot. Yeah, remember how we were talking about every single program uses different keys to move things around? Yeah. Show me the edge on, not the
okay.
The angled view. That one right there, yeah. And yes, perfect. So these little slots right here, the 46.5 millimeters, see how they go in there? Those little slots in the edges of the case are meant to hold a circuit board. So all of my products have used that kind of slot. SOAR has, the Radio Pro does, and well, I guess those are really the only two I've developed. But you're going to just make a circuit board that is wide enough to slide into those two slots, and that will hold it in place exactly like that. Except that you have to turn off your background because it's chroma key.
Because it's a green
circuit board.
Yeah.
My circuit boards are blue. Actually, I guess not all of them, because here's a green one. So in any case, you slide it into that case. And so we're going to be making a circuit board that is exactly the dimensions of this case, right? 46.5 millimeters width there. So we'll probably do 46 millimeters, and give it a, half a millimeter of slop either way so that it's not super tight as it slides in. And then, scroll the page to the right so we can see the length of the box. There you go. So 85 millimeters. So we're going to make a circuit board that is 46 by 85 millimeters. And then the panels on either side. One panel is going to be the metal panel that comes with the box, and he's going to punch a hole or drill a hole in there for the panel mount connector for the headset that he's got, which he's holding up right now. And then on the other side is going to be a square hole for an RJ45, which is the OHIS connector, and we're going to use a circuit board for that panel. So we'll be coming back to this drawing to figure out the exact dimensions of what that circuit panel needs to be, where the screw holes go for that circuit board, and then we can talk about the dimensions of the RJ45. We may not get to the side panel today. We're going to concentrate mostly on the board that actually has electronics. Circuit boards as panels is just a convenient way to make a panel with exactly the dimensions I want, route it out with these holes here, and you can use silkscreen to put text on it. And they're very inexpensive to make, especially when they're less than about 10 centimeters by 10 centimeters, because board fab houses, that's usually kind of their unit. Anything that's 10 by 10 centimeters or smaller is price cheap. For JLC PCB, if it's the first one in an order, it'll be $2 for 5 copies of that board. If it's the second one in your order, it will be $4, and they're all $4, but they give you $2 off the first one in each order. And then you have to pay shipping to get it to you, which is like $20 from China. But that's 2 to 3 day stuff. Anyway, but if you're ordering a bunch of other things, it's still $20. So in any case, it's very inexpensive to have these things fabbed and sent to you. There are also American equivalents of that. Osh Park is the one that I like to use. They only do 3 boards instead of 5, but the prices are about the same for little tiny boards. Okay, so let's get started with KiCAD. Go ahead and bring up the KiCAD window there. And this is the project window. So when you first open up KiCAD, this is going to be the first window that you see. And this doesn't actually edit any of the files or anything. This just manages your project. So you have to go up to File, do New Project, title it. Nope, this is a User Pro. Yeah. Or not Pro, so user side. Yeah.
Yeah, so this will be User Amateur.
User Amateur. There you go. Find a place to put it. Thundersag. Yeah. Ham stuff.
Element stuff.
There you go.
Oh, yes.
Woot. Okay, and so you'll notice that it created 3 files over on the left-hand side. KiCAD Pro, which is short for project, KiCAD PCB, which is your circuit board, and KiCAD SCH, which is your schematic. Okay, so the first thing we're going to do is we're going to open up you'll notice how PCB and schematic are kind of sub-files of the project. The project is like the metadata for the entire thing. And then the schematic and the PCB are the data files for the schematic and the PCB. So go ahead and open up the schematic. And this is going to dump. Okay. This is the first time you run KiCAD. Copy default global symbol library table. Yeah. So it's just setting up all of the data for like what schematics or what components we have and all that fun stuff. You only ever have to do that the first time you open up the schematic program. Schematic hierarchy. Oh, that's new. Oh, neat. Okay. I'll have to spend some time looking at that some other time. Either that or it doesn't default on Linux. Okay, cool. So this is your data page, or your worksheet, your page.
Yep.
There are a lot of different things that we can do here, but primarily over on the right-hand side are all your tools. And the third one down, that looks like a little op-amp. Nope, that one right there. That one is we're going to add a symbol to the board. Okay. I was going to go down and show you what all of the tools are, but let's go ahead and add a symbol.
Okay, well, hang on. We'll close that.
Okay, go ahead and close that. The next one down, so the first one are highlight wires and pins of a net. Is that where that pin is? Okay, anyway. No, go down to the add a symbol. So the op-amp. So yeah, that adds things like resistors, capacitors, chips, connectors, all those kinds of symbols. The next one down, which looks like a little ground signal, those are power symbols. Power symbols are like, plus 5 volts, VCC, ground, earth, et cetera, et cetera. And then that is to add a schematic wire, right? A wire from this pin to that pin sort of thing. That's a bus. Buses are typically used on large digital circuits where you've got lots of wires going from point A to point B, rather than drawing 32 individual wires to connect the 32-bit data bus from one chip to the 32-bit data bus of another chip. You just draw 32 little tags into a bus, and then you can run that bus over to the other one and then break them out on the other side. We won't be using a bus here. Scroll down to the next one. And those are those little, at a wire entry into a bus. Those are the little tags that I was talking about. You got a 32-bit bus. I'm going to draw 32 of those little entries, and then the bus is going to connect over to the other chip. Again.
So in the audio world equivalent, that's a stage snake with the fantail and a stage box on either end.
Correct. Yeah. So for those who don't know what a snake is, it is a... you've got like an XLR cable, an XLR connector with a little thin cable coming out of it, but you've got 8 of those, 16 of those that you need to get from the stage at the front of the house to the mixing console at the back of the house. And you don't want to run, 16 individual cables back there. So you run them, they make what are called snakes, which is a 100-foot long or 200-foot long cable where all 16 of those individual cables get into like one giant shrink wrap. And you run that one giant thick hose from the front to the back, and then, it breaks out into a bunch on one side, and it breaks out into a bunch on the other side.
Right.
So it's exactly like that.
Cool.
All right, move down to the next one.
There
you go. So add a no connect flag. So it's a little X. This is not required, but it's generally considered good practice that if you've got a component that has a pin on it that we're not going to use, stick an X on it, because that tells the system that this is intentionally not used. And a design rules check, a DRC, will sometimes find, hey, you've got a component over here that's got an unused pin. Was that intentional? Maybe you forgot to hook it up. Maybe you dragged the wire over to it, but it's right next to it and didn't actually touch it. And right, so you want your DRC to tell you about pins that are not connected. And if you have a pin that is intentionally not connected, you throw a no connect on it. Junction. If I've got wires that cross each other, I need to put a junction there. Otherwise, they are a jump over. So if there's no junction dot there, then it's a jump over, and they do not actually connect. But if you want them to actually connect, you got to put a junction dot there. Junction dots are mostly handled automatically. Sometimes you'll have to drop one manually, but for the most part, they're pretty automatic. A net label. So when you draw a wire on there, you can label it. You can stick a name on that net to make it easier to understand what the purpose of that net is. If you don't stick a label on a net, then it automatically picks one based on the component name and the pin number. This is like the first component that was laid down was C1, and it's got 2 pins. Capacitor 1, it's got 2 pins, pin 1 and pin 2. If you just drag a wire off of that, it'll automatically become, C1, pin 1. But if you want something that's a little bit more useful, like this is, SCL for the clock for an I2C bus, that kind of thing. You can drop a label on there and make it. It's just something for us humans. Down to the next one. Add a net class directive label. Don't know. Never used it. Move on.
Okay.
Global labels. So a global label is a little flag that you connect to a pin that you put a name on, and now I can put that flag on other pins or wires, and they will all be considered part of the same net. So it's a way of drawing a wire from this component over here to this component over here without literally drawing a wire right through something else. Right? If I want to connect this pin to this pin and there's a bunch of stuff in the way, I could draw a wire, all the way around it, or I could just stick these 2 little flags on there and put a name there that connects the 2. It's also useful if you go between sheets, which we will not be after dark. Anyway, you can have multiple sheets in your schematic, and for big schematics, you kind of need to do that. Putting a label down on there, this is a global label, and therefore a global label is the same across all sheets in the project. And then a hierarchical label, you can have hierarchical sheets. and hierarchical labels, I think, will go down but not up, or something like that. I don't remember exactly how it works. But again, I never use it. Add a hierarchical sheet. Okay, I was talking about hierarchical sheets. We're not going to be doing with that today, so let's optimize that out. In the hierarchical sheet pin. Okay, add text. So if you just want to drop some text on your sheet, on your schematic, like a little note, you use the text tab, and then boxes and circles and arcs and drawing things. So these are all things that you can use to just kind of mark up your schematic. They don't actually affect what ends up on the board. It is purely for the humans that are reading it. Okay. So that is a quick... Oh, you've got it centered on Zoom, apparently?
How did I do that?
Oh, so you're on a Mac. Are you using a touchpad then?
No, I'm using a mouse.
Okay, then I think it's either middle or right button will grab it, and you can drag it. So not right button. Cancel. Yeah, use the middle button, and you should be able to drag the thing back to the center. Yeah.
There we go. All right.
Okay, so let's go up to place a component. Grab the... Yep, that one. First let's describe to the viewers what is the thing that we're going to be designing today.
Okay, so the OHIS standard is something that Mark has come up with, that he's proposing that you have a interface, because right now, if you have a headset and you've got a radio, 99% of the time, you can't just plug them directly in. You can get an adapter from the headset manufacturer sometimes that works with your particular radio. But if you got two radios that have different microphone connectors, you need two different adapters. If you go to a field day and you've got 8 guys set up with radios and you want to just use your headset, you don't want to get ear boogers from other people's headsets, everybody has a common radio side box that's designed specifically for their radio that goes to the standard OHIS connector, which is an RJ45. And you just connect the headset to the radio with a short piece of Ethernet cable. So it becomes a standard connection between, you build a box for your headset input that has the RJ45 on this side. Some other guy builds a box for his headset that does the same. Everybody has a box specific to their radio that all on the outside facing side has the RJ45. You walk around, you can plug your headset into any radio without needing a bag full of adapters. That's what OHIS is.
That's the goal.
So,
yep.
So my plan is I'm going to build this one for my Motorola headset. And I've got another one I'm going to build later. I've got a Heil headset that I'm going to build, but this is my primary headset. And then I'm going to build the box for my Kenwood here. I'm also going to build the box for my Yaesu FT857D that's in my POTA rack. And also I'm going to try to convince our club to build the little radio side interfaces so that when we do field day, we can do this. So that's my project for right now, is to build the circuit board that allows it's, instead of hardwiring everything together, because hardwiring on an RJ45 is a nightmare, because you usually end up having to use something like this, and you got all the separate pins you got to run wires out to, and then punch a panel mount hole and everything. So I just want to use the circuit board mount RJ45 with a little preamp built on the board that's powered by the OHIS cable. And then on the other end, I just plug my headset in. That's the goal.
Yep. Awesome. So I couldn't have explained it better than myself. So that was great. Thank you. I'm gonna start pointing people at you when they ask me what OHIS is.
Okay.
If you're curious to learn more, I have created ohis.org. Who knew that a 4-letter .org was still available, but apparently they were, and thankfully it was the one that I cared about. So ohis.org has been registered and has links to a bunch of documentation there. So if I cover up the star with my fish sticker, will that work? I like your fish sticker. So I want to acknowledge we got some people in the chat room right now. Dan Martin says, ooh, something, because of the title of this. We're working on something. What are we working on? Something so exciting. Marcel is giving his opinion on how it's pronounced. KAI-CAD? Is that Kai? Yeah, I guess that would be, it would not be key, so that'd be KiCAD, yeah. And then let's hear. Daniel Wynn says it's not an RJ45. It's an 8P8C modular. Thank you for channeling Kenneth Finnegan for me. Yeah. KiCAD.
Yes, it is, but everybody knows it as an RJ45.
Everyone knows it as an RJ45. So while that is correct, it is technically correct, which is the best kind of correct, we all know. Where I go back and forth, and RJ45 is not only more commonly known, but it's also it rolls off the tongue a lot better than 8P8C modular does. So, all right, so let's get down to business here and start throwing some components on the board. So hit that up and click that button there and type in, you can search for it. You can either like go down to the connectors, or you can just type in there and filter on it. Search for RJ45. Let's see what it has.
Is it RJ dash? Oh, see, now it has 8P8C.
Oh, that's true. It does. All right, go ahead. I think it also has RJ45 as an alias of 8P8C.
Oh, it does.
Yeah. And no dashes.
Shielded.
The one, yes, they are shielded.
Or let's well, RJ40. Oh, here. See, now they get confusing because
they got a bunch of different part numbers. Yeah.
Here, no LED shielded. I don't need LEDs because we're not looking for a connection.
Correct.
Here we go.
So and you'll notice that look in. Hang on. Don't click OK yet. In the description box there.
Yeah.
Derived from 8P8C shielded. So that basically means that it is just a copy of the 8P8C shielded one that we looked at above. Yeah. You can tell because it's italic. When they're italic in the list, that just means that it's a alias from something else. But
cool.
You can use whichever one you want. Oh, that is new. Being able to select which footprint to use when you add it. That's pretty cool. Go ahead and pick one of those arbitrarily, because the RJ45s you're actually getting are not in this outline. So we're going to start out with a random RJ45. It's very close to that one, but it may be... Nope, definitely not that one.
Okay, let me try the other two.
Yeah. Hang on. Let me go get one and see if it's actually... So the problem is that the ones that we buy off of eBay, the pins are staggered the other direction. So I actually grabbed that outline and modified it and just moved the pins opposite of each other. Ask me how many circuit boards it took getting shipped from China before I figured that one out.
How many circuit boards did it take, Mark?
One, which is one more than it should have. Hang on, I'll be right back.
All right. Also, while he's doing that, my plan with this is I'm putting it's going to be horizontal. I'm going to put a belt clip on here so I can clip it to my belt while I'm seated so that the headset cable doesn't have to stretch all the way out.
You
can add however long of an Ethernet cable you want, because it's just standard Cat5 shielded.
Shielded. Yes.
Or you can probably use Cat6 shielded. They're the same, just as long as they're shielded.
Correct.
And you can use 3 feet, 5 feet, whatever.
Mm-hmm. In fact, it doesn't even need to be Cat5. It could be Cat3. As long it does need to have at least a little bit of twist in there, but the important
is available everywhere.
Yeah, but shielded is kind of important. Okay. You know what? Forget it. This is not important.
Okay.
Grab one of those.
So go with the first one?
Sure.
Okay.
Because if I put it down, yeah, it looks like it's the same outline as that first one, but they stagger the other direction.
Of course they do.
So I think that was the conclusion I came to, but it doesn't matter for the schematic. Now, I usually put the connectors over on the left-hand side because you'll notice all the pins come out on the right of it.
Right. How do we flip that?
Do you want to flip it, or do you want to just drag it over to the left-hand side of the thing?
I guess it doesn't matter. And my brain was thinking the other way, but that it's
okay.
6 of one, half dozen of the
No,
other.
let's do it the
no
way
difference.
your brain does. Okay, so you would use They changed this between 5 and 6, between KiCAD 5 and KiCAD 6. Which one flips which way? And my muscle memory hasn't caught up yet. If you hit X, it will flip around the Y axis. It flips it left and right.
Perfect.
If you hit Y, it'll flip it the Y direction, right? So you can use that to change the orientation of your components, excuse me. You can also use R to rotate it. Hey, look, you're right back to where you started.
Yeah.
Right? So go ahead and use X, Y, and R to put it in whatever orientation you want.
Okay, now does it matter for what we're doing with the one at the top, or
it's whichever you prefer? It doesn't matter.
It makes no difference. We'll just put it one at the top.
Yeah, that's fine.
Done.
So now that you've placed it, so you are still in component place tool. Notice how you still have the little op amp by your cursor?
Right.
Okay. So if you left click on the page again, it'll bring up the component placement dialog again, right? And so we can do that. For what your headset connector is a 4-pin?
Headset is a 4-pin.
Okay.
Yes, and then we need the preamp in there too.
Yeah, but let's do the preamp afterward. Let's get connectors in first. So go ahead and scroll through that. There's a lot of schematic things in here, but the important one for you is going to be CON connectors. But you can see all the different types of schematic components that are in here, right? A lot of it's digital, but there's also a lot of analog stuff and RF stuff and whatever else, right? There's just a lot. There's way too much for us to go through, but we are most interested in connector. Go ahead and look in there. But those are going to be for PC board mount phone connectors, like the 3.5 millimeter or 1/4 inch, primarily. So that's not what we're doing, because yours is not a board mount.
Yeah, electrically, I want the same as like a gaming headset.
Yeah, a 4-pin TRRS.
Right.
But it's going to be a separate physical connector. So actually, if you would like it to look like that, then open up Connector Audio. You got to click on that. And then Audio Jack 4. So just grab one of those and, so that's what the component looks like.
Okay.
And so that is a 4-pin TRRS socket, the Audio Jack 4. Now, you've also, look at some of the other ones below it. So ground, that would be like if the physical case has its own shield that gets grounded, that shows up there. They have ones with various switches inside them, whether the tip or ring one, all those different switches and whatnot. I don't think yours is switched at all. I think it's just got the 4 tabs coming out the back, right?
Just 4 pins.
Yeah, so go ahead and use that component. And then we're not actually going to use, on the board, we're going to use a different footprint. So on the schematic, it's called a component. On the board, it's called a footprint. And a lot of components, the schematic component has a 1-to-1 relationship with the board footprint, but not always, right? This is a generic 4-pin TRRS connector. It could be a 3.5 millimeter TRRS, and even if it were a 3.5 millimeter TRRS, there are lots of different sockets that implement a 3.5 millimeter TRRS socket, and they have different, orientations of where the pins go. They have different footprints. So the schematic.
Go ahead. Then let me ask you this then, since I'm not going to be using a board-mounted connector, do I want to drop a connector there at all, since we're just going to really put solder pads on the board?
So you can drop a generic 4-pin connector, which is just a rectangular box with 4 pins sticking out the side, and it doesn't graphically represent anything. Actually, you know what? Because of the pin names, we probably will want to do that. Come to think of it, because so the way we're going to do this, we're getting ahead of ourselves a little bit. So you know what? I am going to have you go ahead and hit delete on that component there, or backspace or delete or whatever it is. Yeah, and then open up your, drop another component down, go to just the connector section. Nope, up. Yeah.
Yep.
Nope, minimize that. I think connector generic. Oh, yep, there we go. Connector generic. Okay, so these are, 1x4. So that's just a generic 1x4 connector, and you can there is no implied footprint to this. Now, do the little footprint drop down. I think that's new in 70 that, or I've just never paid attention to it.
Pin header.
Fan pin header. That's new to. Oh, it's got the little offset tab. So that's like what's used on a computer motherboard. That's not what we're going to be using. Drop it down again. So you'll notice that there are a lot of different options. We don't want JST. Go down to connector_pin header is the name of the library, the footprint library. There we go. So connector, pin header, 2.54 millimeter. There we go. So we've got a horizontal, which is, the pin comes up from the board, makes a 90-degree right turn and goes horizontal. There's also vertical, which is just, the rectangles. No, don't use the horizontal. Use a vertical. And then there are two different SMD surface mount variants. Because when you have a single row of pins and they do SMD, they stick up vertically, but then they kind of bend out to mount, flat on the board. But when it's a single row of pins, you kind of have to stagger which one goes that way and which one goes that way. And when you stagger it like that, you can start that way or you can start that way, and it's a different outline. So that's why they have the two different SMT outlines. Okay. But this is what we're going to go with here. So these are going to be the pins that we're going to use for that. You probably
this needs to flip, right?
Yep. So X, exactly right. And drop that down. Okay, so let's start with this. Hit escape to get out of component place mode. Now you've got two components on the board. Let me show you how to move them around. Hover over one and hit M. That will move it. So now you can move it wherever you want. And then you left click to drop it again. Notice that because you were hovered over it, it automatically selected it. Okay? Here's the annoying to me part, because it always screws with my muscle memory. You do not have anything selected. Go over to the connector on the right. Click it, but don't move it.
Oh, man.
So click it. Now move your cursor over to the left. So it is still selected. Hover over the connector on the left, and then hit M. Move your mouse.
It moved it back over there.
Because that was the one that was selected.
And it didn't let go until I click.
Yeah, and or hit escape.
Okay.
So if you see me working on these things, I will be hitting escape all the time, because I will have things selected, but when I'm done working with it, it doesn't always automatically unselect it. And so I just hit escape. It's like a nervous tick to make sure that I don't have anything selected at any given time. Tommy on there. Daniel Wynn. Okay. Hey, peeps. Kids are in bed, so it's Friday night shack hanging time. Hey, Vance. Figured I'd watch along. I have thoughts on custom boards for a project that I'll never revisited. So thought this might be inspire. Okay, well, yeah, come chat with us sometime. We would love to inspire people. And Exploding Lemur is here. So the true peanut gallery has arrived. And yes, you are a moderator, Nick, because you were a moderator on some of my very early live streams when I think Kenneth and I were up here causing shenanigans. I am drunk with power. Peanuts and whiskey, is that a thing? Oh, if you listen to Greg, How to Drink. How to Drink is a wonderful channel on YouTube, and he often describes whiskeys as having peanut notes. I'm not a huge whiskey fan myself, at least bourbon, but apparently whiskey and peanuts is a thing. And no, Screwball does not count. Peanut butter whiskey. Oh.
That just doesn't sound good.
Some things are based on a dare and should not exist.
Yeah.
Okay. So movements
I had a college roommate who decided one morning after a particularly long night of drinking that vodka and RC over Quisp sounded like a breakfast idea.
Oh my God.
He told me if he ever thought of that again, lock him out of the room and don't let him back in.
Yeah, I didn't start drinking alcohol until I was 45 years old.
There you go.
I grew up in a recovering alcoholic household. Both my parents were, and they've made it very clear to me that it's okay for me to talk about this. They were both long-time members of AA. And so I grew up going to a lot of AA meetings and watching them. And consequently, I was terrified of what might happen to me if I started drinking. And then as I got older, I discovered that starting drinking at the age of 45 is very different than starting drinking at the age of 18 or 21 or whatever.
You're generally a lot more sensible.
I am mostly past my testosterone poisoning. And yeah, so that's a different thing. But I still 100% respect people who choose not to drink for whatever reason, whatever their reason is. It doesn't matter. I will always support and yeah, anyway. Consequently, I have never been drunk. I have gotten tipsy. I have never been drunk, and I really have no desire to ever do that. Okay, so let's continue on here.
Yep.
But we digress. So the connector on the left is going to be just a 4-pin header that you are going to solder wires to get to the other connector. Let's go ahead and change the name of that. So hover over that and hit V for value. The value in the context of this connector is just the connector name. So, 4-pin headset, whatever. It's just a text value that makes it easy for us to understand. Perfect. Do the same thing on the one on the right and call it OHIS or whatever you want to call it. Okay, perfect. Yeah, I was saying earlier that we were probably going to edit that schematic. We're already, half an hour to an hour in. I don't even know how long our stream has gone yet. We're 45 minutes in and we haven't even started laying down transistors yet. So we're going to hold off on that. So you just have a pinout of the description of OHIS, what pins are on each which signals are on each pin. Let's go ahead and bring that up so we figure out what we have to work with. Okay. So pin 1 is VCC power. So the radio side adapter can provide power toward the user side adapter. We will not be using that for this. Even though we're putting a preamp in here, I will show you how the preamp gets powered. It is not from that power line. Pin 2 is push to talk, which is just a contact to ground. How are you doing push to talk on this? Are you going to have a second connector, or are you going to put a button on the case?
There will be a connector on the radio side because I'll use here in the shack. I use a foot pedal. I hadn't thought about that because I disabled the push to talk on the headset itself when I put in the phase reverse switch. So my push to talk is generally even in the POTA thing. I've got a foot pedal that I would use. So I'm imagining that the push to talk would come off of the radio side.
So in OHIS, push to talk is over the OHIS, and the user side adapter has a push to talk. That's reversed because it's coming from Zoom. Sorry about that.
Yeah.
But on my adapters that I make for this, there is both a socket for push to talk over here, and you can plug in your own external push to talk, or there's a button on the case itself. Yeah, you can see the little button right there. It's just kind of sticking out there, and that acts as a push to talk as well. So you can hold this in your hand, with an OHIS cable, Ethernet cable coming out of this side, and your headset cables coming out of this side, and this becomes your push to talk, like a handheld push to talk.
Well, in that case, I could plug the.
I assume do you want the foot switch going to your waist?
No.
Yeah. So
We would have to deviate from the standard then, wouldn't
Well, no, it just means that you're not going to be using that part of the standard, just like we're not using that part of the VCC, right? So are you going to be using your own radio side adapter, or are you going to be using a Radio Pro?
I'm here at home. I'm going to use the Radio Pro.
Okay.
For the 857D and the Poto rack, I'm going to brew up my own.
Okay. So the Radio Pro does have a front panel accessible PTT pass-through. Oh, shoot. But that's not going to trigger OHIS to go. It's not going to trigger the OHIS audio. Okay. Well, it means that we're going to have to design a second box. Or you'll have to go in and hand hack it yourself.
Oh, great.
When you design your own adapter, you can do whatever you want with the PTT. So I really wish I had one that wasn't mounted in my rack right now. Let me get out a circuit board. Hold on. Nope, not that one. Really? Stuff's falling down all over the place.
I never even considered this.
Yeah, I should have. I don't know why I haven't either.
You know, for the
Damn it.
For the portable setup, I wouldn't mind, I guess, having a push to talk
on the box,
or on a little, a little pendant.
Yeah.
Push to talk. Especially because I mean, I guess setting it, the pedal down on the ground may not be even or really, functional.
Yeah.
So,
all right.
The Radio Pro, though, that I was going to use here at home, you said I can use a pedal, right?
So no. Well, I mean, you can, but it's not going to come off of the Radio Pro. So here's a Radio Pro that's not actually mounted in a box. I just had to dig it out. Let me make it a little bit bigger. Okay. So this is the back because it's got the Anderson. So the back has an RCA, an RCA that's meant for PTT. Then there's a 3.5 millimeter, an RJ45, and the 8-pin round connector, the GX16 is what it's called. These three are meant for microphones, and they're just in parallel, right? It's because things have different microphone sockets. And then this one is for headphones or speaker. So those are the connectors that go to the radio on the back, and you can use any combination of those. Then this here is called the config board, and all pins of all of these connectors show up as rows on this configuration board, right? And so any pin on those connectors, and then signals show up as columns on that board. So like microphone plus, microphone minus, PTT, power ground, headphone left, headphone right, et cetera, right? So like all the signals are columns, all the pins on connectors are rows. So you can literally connect any pin to any signal. And then this column right here, I don't know if you can tell, but it's got a whole bunch of little 0 ohm resistors on it. And those 0 ohm resistors connect the radio side connectors to the pass-through side connectors. And almost all pins are connected through. The only one that is not connected through are the ones that are tied to microphone. And then on the front of the device is the same RCA, the same 3.5 millimeter RJ45 and 8-pin GX16, and then for microphone, and then the 3.5 millimeter for headphone or speaker. And so these connectors are literally just connected directly to these connectors. So all of the cables that go to your radio then have the exact same signals presented on the pass-through connectors on the front of the device, except for the microphone. And the reason for that is because the OHIS port gets, you plug in your OHIS user side device, and it will get a copy of the audio that's coming from the radio. So the speaker or headphone audio comes in, and it gets passed through to the front panel, but it also gets pulled off and sent off to your OHIS port. But the microphone coming from your OHIS port, it needs to be either this microphone or the pass-through microphone. And so the pass-through microphone is like, I've got a really nice Yaesu, and I've got the Yaesu desktop mic. And if I still want to use my Yaesu desktop mic, I can plug it into the pass-through connectors. And when I hit the PTT on the really nice Yaesu mic, that goes through to my radio. But if I hit PTT on OHIS, then there's a relay on here. That little white device right there is a relay that takes out the pass-through microphone and connects in the OHIS microphone.
Okay.
Right? So whichever PTT is used, it sends that microphone through, which means you can't use that PTT to trigger the OHIS microphone audio. So, yes, you can connect a foot switch to this, but if you do that, then it's just going to send the pass-through connectors mic audio, not the OHIS mic audio. You can modify it. I can help you, like if you never want to use the pass-through and you're willing to get rid of that, I can show you how to modify it so that this PTT connector will actually trigger the OHIS stuff. That would actually be a relatively simple mod. But it's not designed for that. It's designed so that the OHIS is the one that gets the PTT.
No, I can't live without, the standard mic. I mean, I wanted to be able to use both. So
yeah.
So,
well, which means
we presented a challenge. We have.
Well, okay. So what it means is, in your particular use case, you want the OHIS to come out, and you want a way of triggering that OHIS, but you want that trigger to stay next to the radio.
Yeah.
You don't want to necessarily prevent a trigger from the user side device. So you can still stick a PTT on your user side device, but you want to be able to also use the trigger that's here. Good news, PTT is just a contact closure to ground. So you can put multiples of them in parallel. In fact, that's exactly what this is. So I have a button on the device itself that is a PTT, but I also have the socket that is a PTT. They're just in parallel. There's no combination logic or anything like that. It is just one of them connects the PTT line to ground. If multiples of them are connecting the PTT line to ground, it doesn't matter because it's just a contact closure.
Right.
So you can do the same thing on yours. So you can make a small box or whatever that plugs directly into the Radio Pro with a very short cable that exposes a PTT socket and then exposes another OHIS port on the other side. And then you can just use that as your OHIS port, and you got a little local PTT extractor.
Okay.
And then if I show up with my OHIS, which has my PTT built into it because I like mine handheld and it's connected into my OHIS adapter, mine will still work, right? You haven't broken anything on the OHIS side. You've just added a little local feature for that.
Okay.
So we can do this.
All right.
Oh, hey, Alan. Sorry, I didn't notice that Alan was had joined earlier. Alan Jones is a friend of mine from a former employer of both of ours. We've used to work together. Really cool guy. Is technically an FPGA. No, it is not an FPGA unless you're talking about something else. Well, they're talking about hooch. It's a chemical formula. Okay, never mind. Anyway. Purdue. So what were we talking about? Okay, so PTT and then okay, so let's go. We've got a huge digression here. I'm going to make our talking heads smaller again. And the screen bigger.
This is what those of you in Ham Radio Workbench called a rabbit hole.
A rabbit hole. We have those. We have many of those. Okay, and then pin 3 is the microphone ground. Pin 6 is the microphone plus, the microphone audio. So 3 and 6 are for microphone. And then you're just going to use 4 and 5 for the headphones. There's also a headphone on pin 8. It's technically left audio and right audio. You can passively mix them, but that has the potential of backfeeding audio into wherever you're getting the audio from, and that's a bad idea.
Yeah, my headsets are mono.
Yeah.
Now, also, if you remember correctly, these share a common between the microphone and the headset. So.
That's correct. So the microphone ground and a headphone ground are separate in the standard, and if you can, it's always a good idea to keep them separate on the user side. You can't, because your headset inherently shares a ground between the two. Same with CTIA, the PC gaming headsets. They also share a ground. So it is explicitly called out in the OHIS standard that power ground, microphone ground, and headphone ground have to be able to be connected together. Ideally, they aren't connected together, but don't ever design your radio side device such that connecting them together causes problems, right? Like, don't make your microphone minus actually be a VCC over 2 bias voltage, right? It has to survive being connected to ground for this very reason. Oh, Thomas is here. Woohoo! Thomas is very excited to try out the OHIS hardware. So, yeah, I assume you got a chance to see the prototype board that I just held up. And Dawn, KB2YSI, thank you everybody for showing up. And James, KI50EB. I'm sure there are a lot of other people that I've missed in chat, and I apologize about that. But
oh, wow, there's people actually watching. The pressure is on now.
That's right. I am doing well. Kids keep us hopping, but everyone's good. Awesome. Yeah, being a parent is a lot of fun, in my opinion, in my experience anyway. So yeah, this is the prototype board. I have just placed orders for, okay, maybe this is going to turn into a sales pitch. I've just placed an order for 50 of these for the early adopter stuff. That all happened this past week. These boards will show up in about 3 weeks, I think. The cases from Hammond show up in 4 to 6 weeks because I'm getting custom cases. They're their standard case, but without a bunch of parts. Rather than throwing away a bunch of plastic parts, I got custom cases without the parts that I'm not going to use. Makes it a little bit cheaper for me, and it makes a lot less waste. I figured that was worth waiting a couple of weeks for. So, so yeah, anyway, in 4 to 6 weeks, I should have all of the hardware I need to start building these things, and I figure a couple weeks after that to get everything built and stuffed in boxes and shipping out to my early adopters. So I am very excited about this. Okay, let's keep moving on. So what we're going to do, the way I like to do this is by putting flags on the pins that we care about. So in KiCAD, go over to the, yes, that one, a global label, and label this one mic ground. Okay, and rotate that twice.
That's R?
R, correct. And stick that on pin 3 of the OHIS connector.
Does it snap?
It does, yes. So that's
cool.
Connected. You can also zoom in if it makes it easier. You can use a scroll wheel to zoom in. It'll center the zoom on your cursor, so make sure your cursor is where you want the zoom to center. All right, let's do another flag. And do mic plus. And before you hit enter, I'm going to have you do one other thing. Oh, I like this a lot better. Down, oh, yes. Up from where your mouse is. Yeah. Do the one to the right. So that will make the flag go the other direction instead of having to rotate it. And put that on pin 6. Okay. And we're going to do another one. Headphone ground. And I think headphone ground is on pin 5, if I remember correctly. I think I alternated these. And then headphone left. And put that on pin 4. Okay. Bring up the OHIS document and make sure we got that correct. Because, of course, it's right over it.
4 is headphone left. 3 is mic ground. 5 is headphone ground. 6 is mic plus.
Okay. And then let's go ahead and tag 7 and 2 as well. So 2 is PTT.
7 is PTT ground.
Yeah. I usually call it power ground, but yeah, that works too. Yeah, PTT ground is fine. Yep. And then 2 is PTT. So the exact labels for these doesn't matter as long as you are consistent. It is any other pin that you put a similar flag on that has the exact same name will be considered to be the same, as if a wire were connected between them. The technical term from an electrical standpoint or electrical engineering is called the same node. It'll be the same node as long with every other pin that has the same stuff on it. Okay, so now that we've got that done, if we wanted to be complete, you could throw flags on pins 1 and 8 just so that they're all labeled, even if we're not going to be putting anything with them. 1 is VCC and 8 is headphone right. We're just not going to be using them. Perfect. One other thing. Stick a earth on that shield pin. So go up to the electrical components. Let's scroll through here and just kind of look at them. Expand out the power and give you an idea of the kinds of power flags they have, right? Bunch of different voltages, positive and minus, names for things. There's grounds. There's various different grounds. There's a ground, a D ground for analog and digital, stuff like that. These are all arbitrary. There's no inherent meaning to them other than what you assign to them. And they're just different names that you get to use for whatever you want. So for shielding, I typically use earth. That's a convention that I created. It's not inherently required or anything like that. So I wouldn't put it right on. Okay, you could do that.
Well, okay.
Because you almost never draw a ground that way or an earth that way.
It's normally pointed down.
Yeah, so go ahead and rotate it again. Point it down and just move it off to the side, just like that. And then this will be your first wire. And yeah, zoom in so it's a little bit easier to see. There you go. And click it. Done. That's it. Now the shield of the RJ45 connector will be connected to a tag that we are calling Earth. And anywhere else that you put Earth will be connected to that electrically.
Now, so I need to tag that?
Nope.
Or the symbol is the tag?
The symbol is the tag.
Okay.
Yeah, that's exactly what the power symbols do. Is that they create a tag just like the global labels. Like they work. I'm trying to figure out if there's any reason I should not say exactly like. I think they work exactly like a global label, but they've got special artwork and predefined artwork and predefined names that are just super commonly used.
Okay.
Okay. And then we're going to do the same thing over on the headset connector. So we're going to put flags on, or labels on the headset connector. I don't know what those... Oh, yeah, headphone left and right, because we're not doing anything with that. Or headphone left and headphone ground, you can just connect those directly. That's a good point. Yep, you beat me to it. Flip that around again.
Now
exactly.
Let me see here. Because the way that connector is wired is backwards from everything we know. The tip is actually shield.
Okay.
And then the shield or the sleeve is actually headphone audio.
You have that documentation in front of you, I assume?
Yeah.
Yeah, it's written. Okay.
So that's pin 4.
So headphone audio is pin 4. So we're going to do pin 1 is tip and pin 4 is shield?
Yeah.
Okay.
Yeah.
That works for me.
So pin 1 then is
ground.
shield.
Oh, that's right. It's going to be the same for both of them.
So it's going to be just ground.
Yeah, just go. Okay. You know what? Let's do this differently. Hit cancel. So the issue for viewers, on OHIS, microphone ground and headphone ground are separate pins, but they have to be able to be connected together. And on the headphone connector, there's only one ground, and it is shared between the headphones and the microphone. So we have to connect them together. Rather than use labels for mic ground and headphone ground, and label them separately on the OHIS side, let's go ahead and combine them at the OHIS side. And at that point, since we are not making a distinction between, and actually power ground or the PTT ground is the same.
They're all the same.
The 4 pins on your connector are microphone audio, headphone audio, PTT, and ground, because
Correct.
the headphones have a PTT button on them, which he's disconnected, but ignore that. The connector has a PTT signal on it.
Yeah, let's wire this
as if it were standard.
Somebody else with one of those headsets could use it.
Yes, exactly. So we've got one ground that is shared between all 3 of those. So go ahead, over on the OHIS connector, delete the labels that we created for all 3 grounds. And PTT ground. Now go over to the power. We're going to drop a power component and use ground. Different than earth. Oh, shoot. Do we want it to be different than earth? Yeah, I think we do. Yeah, do ground different than earth. Okay. Now here's a trick. Before you connect it in there, rotate it. I think you'll have to rotate it 3 times. Yeah, there you go. Now connect it in.
In here?
Yep, exactly like that. Zoom in a bit. Okay. Now, you'll notice that the whole thing is selected still because it's got that faint blue glow. Hit escape to unselect it. Then hover over the GND, hover over the title, and click M to move. And now it'll center. I mean, go ahead and make it closer to it, but it was off center.
Got it.
Yeah, so like that. Okay, now select the component itself, the ground component. Select that. Control-C, Control-V. And one more time. Boom. Now all 3 of our grounds are connected together. Head over to the headphones themselves. And Control-V. And connect it to pin 1. And then rotate it. There you go. Oh, it even takes the text with it. Didn't used to do that. It was kind of annoying. Now it rotates the position of the text with it. I like it. Okay. So now we've got our grounds taken care of. Now, the reason I am keeping the signal grounds separate from the earth The earth on the RJ45 is the shield around the RJ45. And because OHIS keeps headphone ground, mic ground, power grounds all on separate pins, shield is also separate, right? The 3 different grounds are effectively signal pins. They are not a shield. And so the shield is kind of a 4th ground, if you will. What I don't want is to connect my shield on both. It's probably going to be connected to ground at the radio side. What I don't want is to connect the shield to ground both at the radio side and at the user side. So the shield is going to be connected to the case of what we're building here, because that is the shield. And if the connector to the headphones had a separate shield and mic ground and headphone ground, if all of those were separate signals, then we would connect that shield onto the shield of the cable going up to the headset. But because the headset uses the shield of the headset cable as its signal ground, I do not want to connect the earth shield to that ground. So we are terminating the earth shield coming from the OHIS radio side. We're terminating it at this adapter. The shield coming in over the cable is going to be connected to the metal box, and that will be our shield. But the ground going up to the headset, because it combines it all down to a single thing, we're going to use the signal grounds for that, not the shield. That makes sense? Who knows? Okay. So go ahead and put down your other 2 flags down there for, so you got the headphone audio.
Let's see. So 2 is push to talk.
Okay.
Flag. And then 3 is mic.
But plus. Not mic plus. Because remember, we don't want it to go straight across.
Oh, that's right.
We're going to stick a preamp in the middle. So, yeah, it's actually Gozina. The Gozauta is on the other side.
Oh, yeah, you're right. Okay. Yeah. So I want to edit that. How do I edit the text?
Hit E.
Oh, how about that?
Yeah. Gozinta. There you go. Now, why don't we go change mic plus to mic Gozauta so that we're at least consistent. Oh, wait.
Yeah, hang on. That's because there you go. Because it was still selected.
It bugs me every time, but that's the way it works, and that's why I'm like nervously hitting escape like it's a tick.
Okay.
So now we've got our connectors done. Let's draw the preamp in the middle. For those following along at home, this preamp schematic is documented in the OHIS document.
It's down here somewhere.
There we are.
There it is.
All right. So those 5 components inside the OHIS user block are what we're going to be building. The 5 volts and the 2.2K, actually 2.2 is too small. I have to change that to a 6.2, but that's a revision to the document. Doesn't matter. That's on the radio side adapter. You can assume that that's already done in the context of the user side. So the transistor, the 75K, the 27K, and the 470 resistors, and then the 1 microfarad capacitor are the 5 components we need to drop here.
Yeah. Now we need this in my case because the element on my headset is a dynamic.
Correct.
And not a condenser.
Not a condenser. Well, yes. Technically, electrets are condensers because they work on the capacitive principle. But condenser microphone typically refers to like studio condensers.
Yeah.
The microphone equivalent of an electrostatic speaker.
Yeah, and those don't need 48-volt phantom.
Electrets do not need 48-volt phantom.
Yeah.
Studio condensers need 48-volt phantom. Exactly.
Yeah.
Okay, so that's the schematic that we're going to do. I'm just going to do it from memory, so you can go ahead and close that. All right, let's drop a component.
Mm-hmm.
Look for, I just usually do a search for 3904. What, I assume you're not going to be doing this with surface mount. You're going to do this with through holes?
I don't hate myself that much.
Okay. Then, yeah, 2N3904 is probably a good transistor for this. And plop that down. Then click again, and we're going to add 3 resistors. So resistors, again, get rid of your search. No, sorry. The 3904. Get rid of the 3904 text. There we go. Now, you can scroll down and find resistor if you want. Yep.
Mm-hmm.
Oh! Ha, ha, ha! I lied.
They're not there.
They're not there. There is, I can't remember. Because I never go looking for it. I just type R_small is the one that I remember. Where are they? Device. So there's a group called device, which has all the common, resistor, capacitor, et cetera, et cetera. So R_small is the one that I usually use. And okay. So you don't want an SMT. Scroll down to resistor_THT. Yep. And then nope, scroll up. It's going to be one of the ones at the top. No. So notice over on the left-hand side, there's like opto device, then resistor under SMD.
Yeah.
Okay, go down to resistor_THT, which is through hole. And then those axials. And let's see here. That is length, diameter, and pin spacing. So I think...
Your standard 1/8 watt.
Yeah. So I think that's going to be an L6.3. I think those are the quarter watts. Diameter 2.5, and then the pin spacing 7.62, which is 0.3 inch.
So this one right here.
Yeah, either that one
3.6 by...
Click that one and let's look at what it shows. So I think that'll work.
Okay.
That'll work well. And then so yeah.
So I need one off of the emitter.
Yep.
And then one off of the two
off the base. One going up and one going down.
Oh, I could copy and paste, couldn't I?
You can do that too. Although to select it, you need to hit escape because you're still in place component mode. There you go. I think you may have... Oh, no. Never mind. You're good.
Okay. Now I'll need to draw wires in there for those.
Yep.
But, okay, so now the next thing we need is a
capacitor. And if the resistors were R_small, what do you think the capacitor would be?
That would be C_small.
You would be correct.
Hey, I can learn stuff. It's that college education coming through.
That's right. Underscore. It wasn't a good college.
Yeah. All right. And this one needs to rotate.
Yep.
Okay.
And this is a new thing in KiCAD 7. I like it. It is automatically assigning reference numbers as it goes. I like that. 6 doesn't do that. You have to annotate the whole schematic before you can do things. The exact numbers don't matter. It just you're talking about where to connect pins. Yeah. Connect the base to the capacitor. And then each of those resistors to that base node. Yep, R2 and R3.
I can move them later, right?
Yeah. Although move them now because it's easier to move them before you drag wires, because it does weird things with wires.
Oops. They're not lined up.
Yeah, it is.
Is it?
Yeah, it's lined up.
Okay.
So drag a wire directly from R2 to R3. I want to demonstrate something. Not a bus.
Oops.
There we go. So you'll notice how there is not a giant green dot at those two, or at the intersection of those two lines. This is where junctions come in. So R2 is connected to R3, but they are not connected to C1 or Q1. As drawn right now. Yeah. So, okay, hang on. Hit Control-Z. Move it back to where it was. Yeah. I'm going to show you dragging and moving in just a second, but let me finish this up. So right now, the vertical green wire and the horizontal green wire are not connected to each other. They are passing over. Okay. If you want them to be connected to each other, go over to the right and do the little green dot. Yep, that one. And stick a green dot at the intersection. Now they are connected. So that's where junctions come in. Control-Z twice. Let's undo that. Drag a wire from R2 to the green line.
Hang on. Awesome.
You have to go do something?
No, we have a tornado warning.
Oh, no.
Okay, so drag the wire from here.
I can't remember. Which warnings are worse than watches, correct?
Yes.
Okay. If you need to, GTFO, and we'll come back to this later.
Let's see. There's a warning into this area until, it's only 15 more minutes.
Okay.
It says take shelter now in the basement, which conveniently is where I am.
Okay. Rock and roll. Do me a favor and hit Control-S. Let's say
Control-S or Command-S?
Command-S. You're a Mac. Yeah, sorry.
Yep. Okay.
Good. We have saved our progress.
Oh, yeah. Hadn't thought about hitting save frequently.
Yeah, James is like, oh my gosh, are you in a safe spot? Yeah, I'm from California. We don't do tornadoes. You know how everybody else is freaked out about earthquakes? Yeah. Whatever. I've lived through some pretty gnarly earthquakes and they don't freak me out, but tornadoes scare the crap out of me. Okay. Yeah. So the rest of your family is good, Paul? Do you need to go do anything?
No, I think we're okay. I'll send a text upstairs to the wife.
Okay. All right. Oh, James, you're in Oklahoma. Yeah, you know. He
knows tornadoes.
You know tornadoes. My wife's family is from Kansas, and every time we go out and visit them, they always laugh at us whenever we freak out about the tornadoes. But then they come to California, and we laugh at them about freaking out about earthquakes. So it's all good. Watching someone else operating KiCAD reminds me I need to finish some PCB work and order boards. Do it, Thomas. Make it happen. Create awesome things, and then tell us about it. Yeah, okay. Don says he's had a project in that state for a long time as well. I have so many projects that are in that state. It has been a force of will to stay on track with projects for Halibut. Like, this is my day job now. I can't just go squirrel off and do whatever I want anytime I want. This is literally my day job now.
I totally get that, which is why I'm forcing myself to get this project done.
Yeah. And this is, yeah. So anyways, if anyone thinks that Paul is creating a competing product with Halibut, I want to make it very clear that OHIS is an open standard, and I want everyone and anyone to be using it. To me, adoption is way more important than any concept of a stranglehold on the market. And so I want people to make their own adapters. I want people to make and sell adapters that compete with me. I want this to happen. So I am happy to help other people make devices that comply with the OHIS standard. So yes, he's making a device that is exactly like what I sell, but I'm still absolutely happy to do it. Okay. Yes.
I'm going to real quick. I want to run upstairs.
Okay. Go do it.
So where's my thing? I'm going to mute myself. I'll be right back.
All right. Sounds good. Take care of yourself, Paul. All right. Well, I'm freaking out about Paul in a tornado. Let's talk a little bit more about OHIS. Actually, I can also just do a question and answer. If you have any questions for me about what we're doing here tonight, or OHIS, or my HHI, the Halibut Headset Interconnect products, which is the Halibut Electronics product line that implements the OHIS standard. If you got any questions about any of that stuff, please pop them into chat now, and I will try and answer what I can. It should not have been more than a few minutes. Yeah. Dawn, as you can see, this has got 5 components and 2 connectors, and we're 2 hours in? I don't even know how long we've been going now. It's been a while. I have a storm shelter. James says he has a storm shelter underground that you've been in twice this year already. Yeah, that's nice. Yeah, I freak out about tornadoes. So, yeah. Please wait. Okay. Actually, let me see if anybody on Mastodon has done anything. Nope, I've only got old things on Mastodon. Although I guess a bunch of people have been favoriting and or possibly retweeting my post with the link. Nope, not a lot of people, just one. Okay. Well, that's great. Anyway, is it on your website? Can you drop a link in the chat? What are we talking about? If we're talking about OHIS, the link for that is ohis.org, and I've just dropped that link in the chat. My website for my hardware is electronics.halibut.com. I've also just put that link in the chat. So I'm not sure which it is that you're talking about. I have intentionally kept the OHIS stuff separate from Halibut Electronics. Again, OHIS is an open standard, and I encourage anyone and everyone to make products for it, because adoption is very important to these kinds of things. My products, I hope to build and design very good products that will make people want to spend money on my products, so that I can put food on the table. But I am also more interested in making devices that go between the radio and the user. That's really the market that I want to get into. Things like the contesting console, which I will show on the screen now. Once you have a standard interface between the user and the radio, it makes it a lot easier to make devices that go between the user and the radio. Because for me to make a device like the contesting console, which I'll describe in just a second, before OHIS, I would have to make the headset ports work with any kind of headset, and then make the radio port work with any kind of radio, and that just adds a bunch of complexity to it. With OHIS, I have a very well-defined interface that I can design my board around, and that simplifies my board dramatically. And so the contesting console is a 2-user, 1-radio device. You plug in a logger and an operator's headsets here, and they have a little intercom between each other, and they can hear the radio. All right, radio's over here. They can hear the radio, they can hear each other, and then when one of them presses the PTT, that person's audio gets sent to the radio, and it can, either one of them, they both have PTTs, and either one of them can transmit on the radio. But it's great for like a contesting situation where you've got one person logging and one person operating, and they both need to be able to hear the radio. And occasionally they'll need to talk to each other and say, like, was that an L or a F or, whatever, without having to like take their headphones off and go, what? That kind of thing. So that's going to be a product that I'm actively working on it right now. And this is a lot easier for me to build when OHIS is a thing. And they don't need to be my adapters. They can be anybody's adapters. Paul is going to be able to use his homebrew adapter on this because it's a standard, and they should all interop with each other, and it will be glorious. I'm the Enid Hamfest coordinator that watched you at our show in November. Perfect. Okay. That would be a good aviation intercom for a Cessna 152. Yes, that would be another use case for this kind of thing. For the contesting console, it would work well for that too. Okie dokie. Yep, there you go.
That was pretty slick.
I don't think it's what you wanted, what you were expecting to happen, but it worked.
No, but it did the thing. So I need to extend this part over here. Out this way.
And you double click, it'll end it.
And
yeah.
It's not what I wanted to do.
Oh, no, when you hit escape, it got out of wire mode.
I got out of wire mode, didn't I?
Yep.
There.
And
straight
over it. Yep, double click.
Bingo. All right.
So, that's exactly what is drawn in the standard. So this headphone amp, actually I probably should have been talking about this. This headphone amp is designed to work off the power that is provided to an electret microphone. An electret microphone needs a 5-volt or some amount of voltage DC coming from the radio toward the microphone, and then the microphone sends audio back on the same wire for reasons. This headphone amp is designed to use that power coming from the radio, or in our case, the radio side OHIS adapter, to power the amplifier itself. And then there's a dynamic mic on the other side of that amplifier, which is kind of nice. So 75K ohms, yep. The other one is 27. The one, R3 is 27.
No, I didn't want... Now you got to select it and then rotate it.
Or you can just Control Z. That'll work too. There you go. And then value. I usually hover over the resistor and hit V to change the value. 27K. And then R1 is 470. I just know these values because I've been working with this a lot. And then Q1 is a 3904, which is correct. And then C1 is 1 microfarad. Okay. Uh-oh. You just lost power, didn't you?
And it just came back. So if at any point in time, my end of the stream just stops.
Yep.
We'll see.
Okay.
Because apparently there's part of the storm moving through again now.
I believe it. Hit Control S again.
Yeah.
I'm impressed that your internet is still working.
Well, I've got my router and my modem all. I've got UPSs all over this house, so when the power goes out, it's a screaming nightmare.
Yeah. Oh, I believe it. Okay. So the next thing to do is to create those flags or the global labels.
Okay.
Your goes intas and goes outas.
So this then is the mic. So this goes to here.
Mm-hmm.
So I need to do that. And this is mic goes into. Yeah, everything around me is blinking. Ham Shack outline phone just rebooted. Radio came back up.
All right, man. You take care of yourself first. This stream can wait.
All right.
But
yeah, let's see what happens here. All right. Let's see. So then we need to, this is
the mic goes
here.
out.
This goes to the other side of the mic. So this goes to the
Oh, you're talking about the one
goes to ground.
Ground, yeah. And it's the same ground on both sides, so you only need to tag it once.
So I tag it as ground. Or do I put a ground in?
Yeah, put a ground on it.
And rotate it?
No, doesn't matter.
Put it like that? Okay.
Yep, that's fine.
All right.
And then Mike goes out.
Which is... Well, let's put a ground over here while I got that up.
You don't need to.
Okay.
Yeah.
Nope, that's not what I wanted. Okay, here's where we hit Control S again.
God. You want a label?
Yeah. Just right there. Yep. Sorry.
No, you're fine, man. You got other shit on the mind. I get it.
All right. So this is goes out.
James is asking where you are, Paul. Is your state a secret?
No, I'm in Northwest Indiana. I'm about half an hour south of Lake Michigan, 20 minutes south of Lake Michigan. I'm about 40 minutes east of Chicago. So I'm not traditionally in Tornado Alley, but there's a big, ugly storm system moving through the Midwest from like down by Tennessee on up through our area. So
yeah.
Okay, and then this is
nothing. You can actually delete that wire.
Oh, okay. So get out of this.
Yep.
Do this, and then that.
Delete it. Yep. Yeah. And I think that's it. While we're here, I want to show a couple of other neat things that most CAD programs use, but I learned about it here in KiCAD.
Before you go there, though, I have a question.
Yes.
How does that preamp get powered?
Okay, so actually I was explaining this, I think, while you were away. Why don't you bring up the standards document, because it shows this better. Okay. For electret microphones require what is called bias power. So it requires a couple of volts. The definition of how it works is a little bit complicated, but let's stick with the 5 volts. It requires 5 volts on the microphone line through a current limiting resistor. And so on that diagram there, you see the OHIS radio on the right-hand side, and it's got a 5 volt and a 2.2 k ohm resistor.
Right.
That value is incorrect. It's actually supposed to be closer to 6K, so a 6.2 is close enough. So assume that says 6.2. I got to fix the document. Now, that 5 volts from the radio side adapter goes across the OHIS connection, which is the space between the two dotted boxes. So that space between those two dotted boxes is the OHIS cable.
Okay.
Okay. So the dotted box that says radio, OHIS radio, is the radio side adapter. And the dotted box that says OHIS user is the user side adapter. Okay. Right. So you can plug an electret microphone directly into that microphone wire, the OHIS wire, because that 5 volts and that 2.2 are enough to power an electret microphone. They require that power to go, and that DC power goes from the radio through to the electret microphone. Ignore the preamp there, because we're talking about an electret, which is connected directly across those two wires.
Got it.
Okay. We are using that 5 volts to power this amplifier.
Now, let's see. Oh. Yeah. My wife, unfortunately, did not hit Control S as often as she should.
Oh, no. She lost her work.
Yeah, about 20 minutes worth.
Oh, Could be worse.
So she's currently not happy.
Yeah.
So then I want to check something here then, because I'm not sure on the 857, because the standard hand mic is a dynamic. So I want to make sure that there is that on that connector.
It's not the radio. It's the radio adapter that adapts it to OHIS.
So you're saying that the OHIS is going to shoot that power out whether it's coming from the radio or not?
Correct.
Got it.
So
okay.
this is the Halibut radio adapter, and that bundle of components right there is doing it.
So the 12 volts that's coming into that box, part of it gets sent out through that.
Correct.
That microphone line. Got it. All right.
Correct.
I understand that now.
Yeah. So that's all.
So whether or not the radio has the bias, that doesn't matter.
Yeah, that's the whole point of OHIS. Is it doesn't matter what the radio has. The adapter that is built specifically for that radio
has what you need.
Will present a common interface. The radio could be expecting a dynamic with no bias and a very high gain amplifier, or it could be expecting an electret with a bias and about 15 dB less of amplification, because that's really the distinction between the two types of microphones. It doesn't matter what the radio expects. The OHIS port will be a explicit specification.
Understood. All right.
So all right.
This is done then.
That is pretty much done. Yeah.
Cool.
Okay, that's what I wanted to show you. So go ahead and zoom in on the mic preamp. Now, we are going to select some components. So you can start your mouse over on the kind of the left-hand side of R2, kind of above and to the left of R2. And then drag, click and drag down like you're selecting, and go over R2, but also kind of go over part of Q1, but not all of Q1. And release. And okay, it's hard to see because on the stream it doesn't necessarily show it, but R2 kind of has a little bit of a glow, and so does the green wire that was entirely inside your select box. Anything that was completely inside the select box has been selected. But anything that was partially outside of the select box has not been selected. That's because you dragged from left to right.
Okay.
If you drag from right to left, it will select anything that is touched by your select box.
Okay.
So, like, drag, start kind of to the lower right. Oh, no, you didn't. You brought your wire back. Z. Yeah, you didn't need a Control Z. Go ahead and delete the wire over to the right. Yeah. Yep.
Okay.
Delete that. So, kind of drag from from right to left, and just kind of touch a couple of components, R1 and Q1. No, don't fully enclose them. Just kind of touch them, just like that. Yep, like that. Notice now how they are completed, selected, even though you did not completely enclose them.
Right. Okay, cool.
And so, intelligent use of whether you're dragging from left to right or right to left can be used to select parts that you want and parts that you don't want. And those will come up in various different specific situations. Okay, escape out of that because you don't want any of that stuff selected right now.
Okay.
All right. James is showing off by saying he had 77-mile-an-hour winds yesterday. Yeah, no, nope, I'm a weather wimp. There's a reason I live in California.
I don't want antennas folded over my roof.
Exactly. Okay. So normally I would say the next thing we need to do is annotate, but apparently version 7 does that for you as you go along. In version 6, this would be like C1 or C question mark. R2 would be R question mark. R3 would be R question mark. And, so it did not assign numbers as you went along. And so in that case, if you've got anything that doesn't have a number, or if for some reason something has the same number and you need to split it out to the different, let's go look at the tools along the top At the top of the screen. There's one 3 to the right. It's like R question, and then R42. That one right there. Click that. That's called annotate. And it goes through and assigns numbers to components that don't have numbers assigned to them already. You could click annotate. Everything on yours already has annotations. So go ahead and close that. But if you're on KiCAD 6, you will need to click that button, unless you've been annotating as you go along. We have been putting values as we go along, but we haven't necessarily been putting footprints as we go along. Several of these we have, but I don't know that we've done it to all of them. So let's instead go look at the footprint assignment. So a few over to the... No, that's to edit the footprints. We want to go to the one where it's like a op amp and then the little chip. No, to the right. Right. 2 more. That one right there. Run footprint assignment tool. So over on the left are the footprint libraries. So again, remember, a component is a thing on a schematic, and a footprint is a thing on a board. So in the middle are all the footprints, are all the components that we've put onto this schematic and what footprints we want to assign to them. Now, you assign footprints as you are dropping components down. So a lot of things in here already have footprints on them, like your resistors. The transistor already has one, and the 2 connectors already have them. We did not do that for C1, though. So go ahead and... well, it's already selected. So over on the left-hand side, let's go find a library for a capacitor. Capacitor THT. I'm going to mute for a quick second here. Oh, sorry, live stream. Oh, I am so sorry, live stream. I muted the Zoom so Paul couldn't hear me, but I did not mute OBS.
So everybody else got to hear you. You're welcome.
I'm so sorry, live stream. You did not need to hear me blow my nose. Oh my gosh. Speaking of 77-mile-an-hour winds, where is my cursor? There it is. All right, so capacitor through hole. Okay, so now it does not actually show a preview here, which I kind of wish it did. So on the upper left-hand corner of this window, the third icon from the left, there's a little chip with a microphone or a magnifying glass. Click that. Drag it out of the way. It didn't actually replace it. It's just another window. There you go. So now when you select a footprint on the right-hand side, it'll show what it looks like. Right? So these are all... CP stands for capacitor polarized.
These are not.
These are not. So, and those are also all axials. And then there'll be CP radials. So go down to C. We don't want C axials. We're probably going to do a C radial or C disc.
Is this going to be like a ceramic disc?
Yeah.
Okay.
I don't know if you've already picked your components. Probably not, because we haven't looked at this.
I have not.
The main thing you need to look at here is the pin spacing, which is the P number on the far right.
Mm-hmm.
So P 2.5. Go ahead and select the next one down. You'll notice that the pins are the same. The only difference is how much room is it drawing on the board for your component, right? Until you get down to P5, which is 5 millimeters between. It's 2.54 millimeters per 0.1 of an inch. So us Americans, we like to think in 0.1s of inches. So a P25 is actually like a 0.1 inch spaced pins. Those are the capacitors with really close in pins. The P5s are going to be 0.2 inches. P7.5s are going to be 0.3 inches, so on and so forth. So I don't know what component you're going to get, whether it's a 0.1 space or a 0.2 space. Scroll down. I think there's an outline that has 0.25 and 0.5. Keep scrolling. Look for one that has multiples in there. No, keep going. Oh, Oh, maybe they got rid of that in the new. No, there's one. Rect 7. Yeah, that. That would probably do. So that will work with either a 2.5 or a 5.0 or even a 3.5, because then you can kind of do it like, yeah, exactly. So I like that. When I don't know what component I'm going to get yet, I like having options.
Yeah.
Did you select that and save it?
I did.
Okay. And everything else has components in it. Okay. Save your work.
Okay.
Now, the top bar, the green button over to the right. That kind of looks like a circuit board. Click that, and that's going to open up our circuit board program. Files in your documents folder. Yep. Now we have opened up an empty board. So first we drew a schematic. We put components down on the schematic and drew wires between them. Mm-hmm. Then what we just did is we took all of those schematics and said, this component on the schematic maps to this footprint on the board. Right? That was what we just did. And now we've opened up the board editing program, and we are going to import all of those changes and draw a board. So the easiest way to do that is on the top bar, kind of 1/3 from the right. Nope. Over to the right. There's kind of one more to the right. That one right there. So you'll notice how like the left half of the icon looks like a schematic and the right half of the icon looks like a PCB. That does an import from the schematic. There's an error. What's the error? Cannot add C1. No footprint assigned. Looks like you did not assign the footprint.
Oh, shame on me.
Shame on me. So let's go back to the schematic.
Is that a separate window that's here?
It is,
do I switch back?
Yeah.
Okay, so...
Yeah, you should be able to... Yep, exactly.
Okay, so remind me how to get there.
Okay, so there are a couple of different ways. The way we did it was to use the assignment tool, which is the over to the right. It's got the op amp and the chip on there. So like the op amp is the component and the chip is the footprint. So there, capacitor THT. First select the library on the left, capacitor THT, and then go down to, I think it was rect. And it was one that had the two different pins in it. I think it's right at the top of your screen there. Nope, scroll up. I think it was that one. You can double-click it. There we go. Now it actually assigns it. Do you see how it's assigned in the table in the center?
Yep.
Okay. Now you can click OK and save this. And now you can go back to the board editor. Somewhere around here. There we go.
And now
do the import again. Yay, no errors. Okay, and close that. Now you got a whole bunch of components that are selected. Just drop them in the middle. And okay. What were the dimensions of the board?
Yeah, what was that in?
It was Adobe, I think.
Preview.
Oh, no, you're right, because it was a JPEG.
Because it was a JPEG.
Not a JFEG.
That's right. So the board is 85 by, well, let's see, it's 46.5 slot dimensions.
I'd give it a little bit of slop. I would just do 46.
46, so yeah. 46 by 85.
Okay. So the way we're going to do this is we're going to start out by drawing the board. Let's take a look around at this this program. So there are a lot of icons in here. Actually, go ahead and maximize this because you can kind of see both toolbars at the top and it's confusing. Or minimize that one. Yeah, that works too. Either way.
Nope, didn't want to do that. Just make this one a little smaller. Oh, wait, this is the schematic.
That's a schematic. Yeah, go ahead and, and then maximize that one or whatever. So close. There we go. All right, so we're going to look around at the tools that are over here. The toolbar at the top is all just kind of how do you view things, so that's pretty much the same. The toolbar over on the right is, again, we have similar tools to the schematic program, but they are board specific. So instead of adding a component, we can add a footprint. We don't want to add footprints in the board. We want to add footprints in the schematic. So we're not actually going to be adding any footprints here, but we can draw... No, we've already got them all in the schematic. So we don't need to bring that up. Unless there's something else you're looking at.
Nope. Okay.
Okay.
So
let's keep looking down at these tools. So that's how you put down a footprint that is not in your schematic. We're not going to do that yet. The next one down is to route a trace. So that's how you draw copper from pin to pin. That one is tune the length of a single trace. We're not going to be doing anything. We're not doing anything complex like that. If you need to add a via to the board, this is a tool for that. A via is a connection from one layer to another layer. This is a filled zone, and so we would use that for... we're actually going to use that for our earth node, which is a shield. And so we're just... anything that is not a trace, we're going to fill with copper, and we're going to connect that copper to the earth, which is, the shield of the RJ45. And so it's a way of doing what's called a copper pour. I'm just going to pour copper over the entire board. Anything that's not a trace will be shield. And that's a keep out zone. So if you've drawn a copper pour and you want to draw an exclusion zone on the copper pour, you use that tool. It can actually do a lot more than that, but I'm kind of summarizing. And then now down here, this is all just artwork. Draw a line, draw an arc, draw a square, draw a circle. You typically don't do those on the copper layers. You would do those on like silkscreen layers. And then we'll talk about layers in a second. But yeah, otherwise those are all just a bunch of artwork tools.
Okay.
Now the layers over to the right. There are lots of different layers that we can work on. The top and bottom copper, front copper and back copper. That's going to be the top and bottom layer of our boards. So we can draw on each of the layers individually. One thing you can do if you ever set this up for a multi-layer board, you'll see more layers show up in here. I typically work in 4-layer boards, and so there's a top copper, a bottom copper, and then an in 1 and an in 2. Those are the 2 inner layers, and you can draw traces on any of the 4 layers. And then you've got front and back adhesive, front and back paste, front and back silkscreen, front and back mask. Those are all different things that are used for assembly of the board. You're not going to be doing anything with adhesive or paste. You are only going to be working on silkscreen and possibly, actually, definitely mask. We're going to do something on the mask. The mask is the solder mask, like the green goo that's spread out over the copper. Excuse me. We are going to be removing that solder mask from the little bit of the board that goes in the slot on the edges so that the board will have an electrical connection to the case itself. And we're going to do that on the mask layer itself. But the silk screen is just the white text or graphics that show up on the top or the bottom of the board.
Cool.
Okay. And then there are a bunch of other drawings, layers down there. User drawings are, like if you want to draw some reference lines or something like that, they don't show up on the board at all. They're not part of manufacturing. They're just there for us to look at what's going on the board, and, you can add measurements to it or whatever you want. We may or may not be using those right now. And then user eco 1, I don't know what any of that stuff is. Edge cuts is the one that we're going to use to draw the edge of the board. Edge cuts is where the router is going to go to cut out the PCB at the fab house. So go ahead and select the edge cut layer. So just click on it, and you'll notice how the little arrow pointed to it. So now we are drawing on the edge cuts layer. Go to the rectangle tool. We're going to draw a rectangle. So, no, you're not. So click a corner, start kind of in the upper left-hand corner, and then draw it down. Oh, hey, look, it's giving you dimensions right there. So make it 86 by, what was it, 85 by 46?
No, 86. No, you're right. I think 80.
Yeah, okay.
Interesting. It snaps to a grid.
Yep, hit escape. Okay, let's go talk about grid.
Let me double check the dimensions. Which is under...
It was preview.
Preview.
85 by 46.
85 by 46. And back to... Nope,
so close.
Not that one. Wait. What did I
don't know.
What did I do? There it is.
Okay.
Okay.
So let's talk about the grid. Over on the left-hand side, you see the mm with the arrow, then the mil with the arrow, and the inch with the arrow, IN. So that is saying which units do we want to use, millimeters or mils or inches. So since we're going to be talking about a 85 by 46 millimeter board, we're going to go ahead and select millimeters, but that just tells you what the numbers show. That doesn't actually change your grid. Your grid is a drop down on the right hand on the top of the screen. So it's the third one over from the left, and you have lots of different options for grids. The metric grids are at the bottom, and the imperial grids are at the top. So yeah, go ahead and do a 1 millimeter grid because our units are full millimeters. And are you dragging or did you click? Nope. You want to click a corner. Ah, so close.
How about I select the rectangle box
Yep,
first?
there we go.
Okay, so 80.
85. Yep.
84, 85 by
46.
46.
Cha-ching. And that is our board. Because we drew that on the edge cuts layer, that is now the perimeter of our circuit board.
Okay.
And you got a bunch of components in it. So now they're laid out just in a arbitrary, hey, let me make the components available in your program. But now we're going to go lay out those components and make it work for what we're trying to do.
Okay.
So let's see here. Most of those components are laid out are using imperial units, and I'm an American, and I'm a dirty American that doesn't like metric, so I still typically work in imperial units. If you want to work in metric, we can work in metric. If you want to work in imperial, we can work in imperial. Do you have a preference?
Makes no difference to me.
Okay. All right, then let's stay where we're at. 1 millimeter grid may be a little bit too coarse. I would change that to maybe a 0.5 millimeter. When I'm working in Imperial, I typically use the 0.025 grid, and you know that's between 0.5 and 1.0 millimeters. So the 0.025. No, stay on 0.5 millimeter. No, that's 0.025 millimeter. Do you see how that's super tiny? That's a 0.025 millimeter. I'm talking about a 0.025 inch.
Oh, yeah. See, you forgot that we're talking different words here.
Yes.
So those are all millimeters.
So it's millimeters on the left with an imperial in the parentheses. And that's
I got it. I got it. So
that's because we have millimeters selected as our display units.
Here we go. 0.25 right there.
Yeah, so that's like a 0.63.
Okay.
If you're going to do that, you might as well switch your units over to imperial.
Or as Vince says, freedom units.
Freedom units, exactly.
Yeah.
Quarter inch. No, 0.025. Quarter of a tenth of an inch.
Okay.
All right, so let's zoom in so we get a more detailed view of this. First thing we're going to want to do is we're going to want to take the RJ45 over to an edge. So select the RJ45. And the same keys are usable here. Not X and Y. You can't flip the component. You can move it to the bottom of the board but you can't just like flip the orientation of the outline without also moving it to the bottom of the board. But R does work, so you can rotate it.
That's assuming I know which side has the hole.
Yeah, that's a good point. For the purposes of what we're doing, since off the stream we're actually going to load a different component on here, don't worry about it. I think it's... Oh, shit.
Like that?
Yeah, I think so.
Okay.
And you want it to stick through the panel, so actually drag it closer to the edge of the board so it sticks out over a bit. I would put the big blue circles. Those big blue circles are going to be holes underneath the board through which the little plastic plugs go in. So get that, I wouldn't say as close to the edge of the board, but pretty darn close to the edge of the board.
Like that?
Yeah, that's probably pretty good.
Okay.
All right. And then so your audio socket is going to take up a bunch of the left-hand side of the board now. So find a place to put your 4-pin headset connector.
It should be okay here.
I would feel more comfortable rotating it and putting it off to the side, because then we don't have to measure how deep your audio connector is and then risk getting that wrong.
I don't want it too close to the edge because we've got to leave room for the slot.
Actually, and actually, you know what? Move it over to the OHIS side, because over there seems a lot better. And then we'll put those the amp components right behind the RJ45.
Okay.
Yeah. Okay. Yeah, move that over there. Okay, now what you're doing now is a bit of an art form, which is laying out the components, the footprints.
So the traces aren't ugly.
Yes. Laying it out so the trace lengths are as small as possible, or as short as possible, but also so that you're not like having to do any finger gymnastics to be able to get components into where they belong. Right? So one of the things that I like to do is I like to keep all of my resistors lined up kind of like they are now. We may want to change the order of them or possibly rotate them, but I like them when they're all kind of lined up like that, because it's cleaner on the board and various other things. Now we know that the capacitor goes between the audio connector and the amp. So move the capacitor between the 4-pin connector and where the amp is going to go, right? Because we know that the audio has to pass through the connector before it gets to the amp.
Yeah. So like there.
Yep. Now you see the kind of the vague lines, the very faint lines that it's drawing? Yeah. That's called a rat's nest. The rat's nest is this pin needs to talk to that pin. And they just draw straight lines. That's not where the trace is going to go, but it helps you lay things out so you have the shortest rat's nest lines as possible, and to prevent crossing over, right? Because anytime you have a rat's nest line that crosses like this, you can't do that on the same layer of the board, so you'd have to go to the other layer of the board. And if you have too many crossings, then you have to really go through some gymnastics. So what I would do is I would actually look at the schematic. The schematic is laid out pretty well so that you don't have any crossed over wires or anything. And it will...
Oh, wait, I see what happened here. That went full screen. And this is over on... Okay, so I'll just have to swipe back and forth.
Yeah.
Okay, so...
So R2 and R3 are going to connect to the base of the transistor and to the capacitor. So I would grab R2, and as you drag it over there, the rat's nest will kind of follow it. Aha! So you see how the wires are crossed right now? The rat's nests are crossed? Hit R twice on R2. And now they are no longer crossed. Now, you also notice that the rat's nest kind of moved over toward the RJ45. It will connect to whatever other pin is closest to it. So the pin on the right of R2 is currently closer to the same pin on the RJ45 than it is to the pin on Q1. But if you drag it closer to Q1, that rat's nest will move over. So it's basically like this is the closest other pin on the same rat's nest.
Right? And then let's see.
So that's R2, which goes...
R1 goes on the other side. That goes to...
No. Don't use these numbers here because those numbers are different than what's in the in the KiCAD
so the
schematic.
75 goes to the collector. Nope, that's not what I wanted.
Oh yeah, drives me up the wall. Yeah, you gotta select the component itself, the footprint.
And this could probably be rotated.
Yep. Yep.
And then this one is the 20. That goes on the other side, so that should go in here.
Yep. Well, select it and move it. Again, not the number. Yep. You got it. Yeah, that works. Does the bottom pin of that go to the center of Q1? It does.
Yeah, it does.
You may want to rotate Q1. No. Have it the way...
Go back the other way.
I think you want it like that. Take R2 and rotate it and put it next to and to the left of R3.
Like there?
No. Next to it, to the left of R3, between R3 and the transistor. Zoom in some. Oh, shoot. Those rat's nest lines are not very bright. Okay. Bring in R1 closer to Q1. And like make it in line with everything else, kind of lined up. Okay.
Okay, so that's connected from there to there and then over to there.
Well, so is that ground? That is ground. Okay. Back up. Select the entire thing, or not select, view the whole thing. So in the upper bar, there are a bunch of magnifying glasses. There's a plus and a minus, and then the one to the right there is zoom to fit. So that will put the entire board in there. Okay, let's draw our copper ground. So go over to tools on the right. The copper pour is that one. Select that tool and go to the upper left-hand corner. And I go a little bit outside the board. And click. And it's going to bring up a dialog. So, because we had edge cuts. Deselect edge cut. And select both front and back copper. Ah, shit. Okay. Because it thinks you're trying to do an art zone, not a copper zone. Hit cancel. Okay. Go select the front copper layer. Now do the same thing. Click a little bit outside the board and...
Oh.
Yep. Nope. Don't select it. Just click there. So you're starting a zone. Okay, now select both front and back copper. So we're going to do pours on both sides. Then we need to select which net... Oh, fuck. We're going to do earth, not ground. Yeah, select earth because that's the shield. Okay, then there are a bunch of other numbers here that we are not going to bother with right now. The defaults are fine on everything else. Now, you're in the middle of creating a zone. Drag over, or don't drag, but move over to the right. You're going to draw a box around the entire page, or around the entire board.
Oh, so go click
Yeah.
And let's move you out of the way.
And it does not need to be a perfect box. That's fine. It can be all hey wonky and whatever. And then just double click and that'll end it. Okay. Now hit the B character. Just hit B.
Let me get back. Okay.
There we go. So, yeah. And I forgot, that's not actually going to solve our ground problem. Okay. How pedantic do I want to be about this? Okay. Let's do it this way. So this is the shield from the RJ45, right? And so we want it to attach to the metallic case. Right now, what we've done is we have drawn copper all the way out to the far edges of the board. So right now, the board is just a solid plane of copper.
Right.
With the only holes drilled around the pins for all these components. We want to expose that copper
on the edges.
On the edges of the board. So to do that, we are going to draw yet another zone, but instead of on the copper layer, I want you to go to the front mask layer, the F mask right there, and then start in the upper left-hand corner.
Anywhere?
This one
or
is probably...
inside?
Well, no, because we do want it to go all the way to the edge of the board. So start there and select both the front mask and back mask. And then hold on. Let me see if there's anything else in here. Solid fill, corner smoothing, none. Yeah, that's good. Click OK. And then draw a box that's about 1 millimeter tall. And go off the edge of the board. No, okay. I'm sorry. We'll just do, let's see here, 0.05 inches. So go all the way over to the, to the right of the board.
Okay. I had anchored a point. So
yep, that's fine. That's fine. So
okay.
you're gonna keep drawing. Oh, did you hit escape?
Oh, I'm sorry. I misunderstood. Okay, so there. Yep. I'm going to draw over there.
Yep. And then you want to go, down. We're gonna draw over the board by 2 clicks. So there, it's 2 grid clicks. So one
click, two clicks.
Yep. Now drag that back over and finish off the rectangle. This line does need to be straight. And then double click right there and that'll end it. Okay. So now that is on our mask layer. And anything that is drawn on the mask layer removes mask. So it assumes that the mask is solid.
Except there.
Except where you're drawing on the mask. And where you draw on the mask, it will remove the mask. So by putting that zone on that part of that board, it's going to remove the solder mask from the edge of that board. We want to do the same thing on the bottom.
Can I copy and paste?
If your box had a straight top edge, yes, and it looks like it does. So yeah, copy and paste that.
Okay, so C, B.
And then, make it overlap by 2 grid clicks. Yeah. So the board was drawn with millimeters, not with inches, so it's not perfect, but that's okay. It can be a little overexposed. That's fine. 1, 2. Right there. There you go.
Okay.
So that will expose the copper on the edges of the board so that they will touch the metal of the case when you slide this into the case. And that is the earth. That is the shield coming in on the RJ45. But for the audio connector, we actually want to use the ground signal.
Correct.
So what we're going to do is we are going to draw another copper pour. So go back up and select the red layer, the front copper layer again. And then go back to the ground pour draw command. So no, not the rectangle.
Oh, okay, yeah.
The zone.
which is
right below the yellow circle.
Right there.
Yeah, that one. So we're going to draw an arbitrary shape around all of this. Go ahead and make it square, but
how far out?
Far enough to be complete, but not farther than it needs to be. So I would move it to the left. Dang it. There we go.
Right.
Now move it farther to the left because we want to include R1 in this.
Oh.
Right? Okay. So start your zone there, and we can adjust the shape of the zone as well. And we're going to do both front and back, and we want this one to be tied to ground. And hold on. It already increased the zone priority level. I didn't notice whether the other one was 0 or 1. So zone priority level basically means if I've got zones that overlap, which one takes priority? If they're the same priority level, they'll just butt up right against each other. But if one of them is a higher priority level, then it will win the keep out. And then there's a clearance from that zone, which is one of these numbers here. There's a clearance right in the middle. From the edge of the zone, it'll go out clearance amount of space and prevent anything else from going in there. But whichever one has the higher priority is the one that wins. If they are the same priority, then neither of them win, and they just butt up against each other and touch, and that's not what we want to do. I can't remember. In version 6, it defaults to zone priority 0. What I can't tell is whether that 1 is there because it says, hey, you're drawing over an existing zone, I'm going to make this one take a higher priority, or if the other one defaulted to 1 now, and I can't remember. So why don't you go ahead and increase this to a 2, just in case. There we go. All right, so now draw an arbitrary shape. You're just going to be clicking on the corners.
What I'm including just the parts?
Yes, but including the signal pins in the RJ45.
Oh, I already clicked once.
Don't worry about it. Don't sweat it.
All right.
Like right there is fine. Then move down. Nope, not that far because we want to include the signal pins in the RJ45. So go to the top of the. Remain for no. Keep going straight vertical from where you are, but stop at like right there. Then go over to the right. Yep, like that, and then go down. Yep. And then now you can probably go all the way over. And like that. And double click. Okay. So now the square, perfect. So the square dots on the corners you can grab and you can drag them around. So like grab escape because you're going to draw another tool. Oh, nope, you got it. Okay. Yeah, perfect. Now hit B again. B tells it to refill all of its zones.
Okay.
So notice how we gave this zone a higher priority. So it is the rectangle, and then it fills up its entire space, and then the lower priority zone is kept out of it on the outside of it, and from the clearance space.
Got it.
So now all the electrical grounds are tied to this plane, and we don't have to worry about ground anymore. We can just draw our signal pins.
Oh, cool.
Which is a little bit easier. So hit escape to deselect it. Okay. Also, it's kind of a pain in the ass to draw traces when you got the ground planes there. So over on the left-hand side, they're the same. Go down. Yeah, that one right there. So that is where we're selected right now. That shows the ground plane. Click the one immediately below it. And that will hide the pores. We can still see the zones, but it doesn't actually show the copper of the pore, and it makes it a little bit easier to see what's going on. Okay. So now we have fewer rat's nests. And I think this will be a little bit...
This one right here is showing that it's connected to ground. This one is showing
exactly
connected to ground. The capacitor is Cool. Okay.
The capacitor is not connected to ground, but
correct.
Okay. So now I think we're ready to start laying down traces. We're finally there. So the trace tool is right above or right below the put down a footprint tool. Nope, not graphics. Yeah, trace. A trace is different than a graphic. They both put lines on a layer, but they do it very differently. So select the trace tool, and let's grab grab one of the pins from C1. Click on it. Okay. So in this case, it's highlighting the pads that need to be connected to that net. Right? So, lay that right there. Do the same thing with that one. Now, okay, is there anything that's going to go to pin 3? See how the red line you're drawing is crossing over a rat's nest that goes up to, I can't tell which resistor is which.
It's coming, the rat's nest is coming from this one right here is coming from the capacitor.
Correct. But notice how pin 1 of R2 also has a rat's nest that I think goes to pin 3. And you're crossing that rat's nest.
We don't cross the streams.
You want to minimize that, because then now you've got to find a way of routing that around. Whereas it's a lot easier to route that trace around the back side of the transistor, the left side of the transistor, to come into pin 2. So you can just go straight down from there. You don't even have to go that far. But yeah, that works. Right? And so that connected those two pins.
Oh, that's true. That box is just an outline. That's nothing.
Yeah, that's called a courtyard. The courtyard is supposed to be for, don't put other components inside this. It's kind of a keep out zone for other physical components. Okay, honestly, I usually ignore them.
We go here.
Yep.
So this one needs to go here.
Yep.
And it also needs to go here.
Yep. And you'll notice that when a trace connects 2 pins, its rat's nest goes away.
Where is this? Oh, this one goes here?
Yep. And to the one immediately to its right. So it'll highlight all the pads that it needs to go to.
Oh, okay.
Right? All right. And then...
And this one is just going to ground.
Wait, do that again? Yes, you're correct. Yeah.
Okay. And this one's going to ground.
Yep. And so now we have PTT and headphone left. Come up and over. Bingo.
And ground is connected to ground.
Yep. So what we are going to do now, what you just did is perfect. From an artistic standpoint, I would probably clean up that trace between C1 and Q1. But electrically, what you've drawn is exactly correct. So if you get out of the draw tool,
okay,
just by hitting escape, yeah. So zoom in over that wonky trace so we can see it better. Hover over a joint. Probably not that one, because that's ones that we're going to keep. That one right there. Now hover over each of those tracks, and it'll show you, because there are 2 different tracks over that joint, right? See how one that goes this way out of the joint and one that goes that way out of the joint. So you can select which one of those you're going to do. But go ahead and select one, and then hit G. G for drag. And now you can drag that joint wherever you want it to be. And you don't even have to select it first. You can just hover over the joint and hit G. Yep. You got it. Yep.
That's prettier.
That's prettier. All right, let's clean up that silk screen. So all the yellow stuff is the silk screen. Most of it looks pretty good, except for that R2 and R3. So you can, if you click on the reference, so the actual text, now you can M and move it. No, that's the wrong one. So you see how the little purple line drags it down?
Yeah.
It tells you which one it's connected to. So that's actually R3. You can put it inside the component, but that makes it hard to see once the component goes in.
Oh, yeah.
So
okay.
I like to drag it outside. So grab that. Oh.
So but the gray lettering is not.
The gray lettering is a piece of crap and needs to go away. That is on a different layer that doesn't show up on anything, but it still gets in the way of selecting things. Yeah, that's a great location for it right there.
Q1 is okay. R1 is okay.
Yeah.
And C1 is okay.
Yeah.
All right.
So the only thing I would recommend at this point is notice how the PTT and the headphone audio pins leave the ground zone that we drew.
Yeah.
Right? So why don't you select the edge of the ground zone.
Down into here?
Yeah. Or just select it. The edge, the zone. Yeah, it's kind of a pain in the butt. You have to be right on the line. There we go. Grab that circle dot in the middle and drag it to the right. That drags the entire line. Bring it a little bit closer. There you go. Because we want to make sure it has enough space. But at the same time, we want Earth to dominate. So grab the corner in the upper right there and drag it to the left.
Like that?
Yeah, that looks pretty good. Drag the corner at the bottom of that line and drag it to the right one click. I think it's one, maybe two clicks, just so that it's parallel. One more. There we go. That's at a 45.
Yep.
All right, hit B. And it's going to refill the zones. Now turn your zones back on.
And
Control
S.
Okay, Control S.
Yeah. All right.
The tool over on the left-hand side to turn the zones back on, right above it.
One?
No, that one turns them off. That one turns them on. Okay. So now we can see how it's poured copper around the traces.
Yeah.
That is pretty snazzy looking. But the bottom layer copper and top layer copper are only connected where there are pins that go through the board.
Right.
But that leaves like this giant area in the middle.
That's not connected.
Well, it's connected through the top of R3. But that's only one spot it's connected. It would be better if that were connected in multiple places, especially when you're in an RF environment. So we're going to do what's called via stitching.
Okay.
So the via tool is kind of the orange circle over on the right-hand side. On the right side of the board. No, not that one. That shows kind of near the top. Click that. And then we're on the top copper layer. So zoom in a little bit in that area.
In here?
Now in where the components are. Okay. And I like adding vias at the extremes of a copper pour. So that corner right there is a great place to put a via. And yeah, like that corner right there. Yes, exactly. And when you've got these long strips here, they kind of look like antennas. And so you really don't want that to be, that's a fine spot for a via right there. Even though it's close to the edge, it's okay. And so you want those to be tied to ground as solidly as possible. Now, those ones are going to be stitched using the pins of the RJ45, so you don't have to worry too much about that. But I would do one a little bit farther to the right, because anywhere you have that narrow spot of a ground, I would do a via on either side of that just to kind of make sure that it's solidly connected to the bottom layer. And so we can stitch all the way around the outside like that, and that's really good. Yep. Now we also want to do the bits on the inside. Anywhere that like it looks like a finger, right? So just north of Q1. So see how that copper area kind of looks like a finger? I would move down closer to Q1. Get as close to Q1 as you can without like overextending yourself, like right there. Yeah. and then add one right there. Yeah, right. And then you've got more space kind of between C1 and the connector that isn't connected to anything, right? So I would actually, in that little, the mountain area, kind of looks like a mountain between C1 and the connector. Yeah, you can't see my cursor, unfortunately, so I have to give this to you verbally. Yeah, that right there. And then there's another one down in C1. Yep, right there. Right? So, like, vias are free. You don't want to go too overboard with vias, but what you've got right now is about the right density.
Cool.
And there's, like, another spot over by the RJ45 in the center there. Yeah.
Right, like right in here.
Right in there. And then underneath R2 and R3. There's another, no, I'm sorry. Underneath the components. So, like, yeah, right in there and over by Q1 on that ground area. Yep. You got it. Exactly. So that has via stitched the ground trace. So now the ground between the traces on the top layer, and it's a solid ground on the bottom layer, except where there are pins going all the way through. But there aren't any traces cutting up the bottom layer. So that is a solid ground. That'll make a really good shield on those electrical connections. All the traces in there, it is going to be very difficult for electrical noise to get in there. Now, our earth shield outside of that zone, we should be doing a similar via stitch on that. And they don't have to be super close together. You can space them out a bit.
And this area is the bare copper, so I should leave that alone.
So
right?
Either way, I personally do it a little bit outside the bare copper, just because I don't want, like, as I'm sliding it into the case, I don't want the holes for the vias to get stuck on anything. Right. So that's why I'm doing, when I do it that way, I usually do it just a little bit outside. All right. The chat has died down a little bit, but we still got 5 viewers watching.
Wow.
Yeah. Are you guys, y'all enjoying this?
You still awake?
You still awake? I mean, it's only 8 o'clock here on the West Coast. That means it's 11 o'clock East Coast time.
And 10 o'clock my time.
James is getting all zen with it. Visualize the traces. I think he typed that when we were looking at rats' nests. Yep, you got it. And I would also stitch the area for Earth underneath the RJ45.
Like in here?
Yeah.
All right.
Yeah. And then maybe do a few of them.
In this middle of this area?
Yeah. And also kind of at the edge between Earth and ground. Yeah, like right there. I just randomly place them. Yeah. That's it. You, my friend, have laid down a circuit. You have figured out what components you're going to use. You have put those components on a board. You have designed the board, and you have laid all the traces between them. The only thing that's left to do now is to put some cool artwork on the circuit board.
All right.
You want to do like AR Newsline, or
sure,
I'm a Hamilton fanboy, or, you know, you got to come up with some cool artwork.
Yeah.
Every single board I design has my little halibut fishies on it.
I'm going to say I don't have the little fish, so I gotta think of what to put there.
Yep. Control S.
Yeah, I did that already.
Okay, good.
I mean, for right now, I guess you just right now just put my call and stuff. I don't know what to put on there yet.
Okay. Yeah, call sign, name.
Well, if I'm going to put graphics, what format does it need to be?
So it depends on whether you want to try and draw it inside KiCAD, at which point you've got lines, arcs, squares, circles, and arbitrary, outlines. You can also, and actually it looks like they may have included it, go over to the right-hand side. This may be new in KiCAD 7. There's a little, that. Click that.
It said something about adding a bitmapped image, so...
That is included in 7 now. That used to be a separate tool in 6. The way it worked is you would import a bitmap image and make it a footprint. And then you would put the footprint on your board. But it looks like looks like it's part of KiCAD 7 now.
Well... yeah, maybe it doesn't understand JPEG.
Or PNG.
PNG.
It may need to be a BMP.
So I'd have to convert it.
Yeah.
So I could drop. I've got some simplified Newsline graphics. So I would just convert one to a BMP, and then drop that in.
Yeah, probably. You can also put text on there.
All right.
Your name, call sign, whatever else.
So what layer is that on? That's
so that'll be on either front or back silkscreen. Yeah.
Okay.
Neat trick. And the way I usually do it with my fish is you can also draw on the mask layer, front or back mask. Just like we put that zone on there to expose the copper on the top and bottom, you can also put text on the mask, and that will expose the copper underneath. And depending on who you use for manufacturing, it usually ends up getting tinned. So it'll show up as like a silverfish. Silverfish, exactly.
Mm-hmm. All right. Well, I'll work on converting that because we got to revisit this with the new connectors. So I'll have one ready by then. Awesome.
So if you don't mind taking a little bit of Q&A, actually, if we're done here, go ahead and save this and stop your screen share, and we'll just stream the two of us. Our talking heads.
Done.
And there we go. Okay. So James asks, are you actually going to be bringing this to manufacture? What are you planning on doing with this?
I'm manufacturing. I wasn't. I was planning on making what I needed. And then if any of the guys in the club wanted to use these, to experiment with, or if they, clearly I not trying to, outsell the radio or the User Pro. But if somebody wants to play with these, I mean, I'm clearly going to have more boards than I need.
Yeah.
So, but I wasn't planning on making these as a business. I don't know.
So,
because manufacturing stuff is I mean, running your own business is, as Mark knows, not necessarily fun.
It's a business. It is not. Yes, exactly. It's still a job. Whether it's a job that you enjoy doing, which it certainly is for me, it's no longer a hobby. And that is a transition that you should not make lightly. You should definitely.
No, my wife and I used to own a stained glass studio, and we finally decided to go get regular adult jobs where because that's your own business is a lot of work.
It's a lot of work. It's a lot of risk. When you're working for somebody else, you get a steady paycheck, you get insurance, you get all the things, right?
Yeah. And I mean, what I'm doing here is just to fill my need.
Exactly.
And it, as we learned, it doesn't necessarily provide anything special that what, you're doing does.
Yeah.
So yeah, I'm just doing these for me. And if anybody in my club wants to, cover the cost of a board, I'll show them which box I bought off of Amazon.
Yeah. Yeah.
And,
so it sounds like you're going to be doing just enough for your own needs, but there's nothing about what we did tonight that is proprietary, right? Obviously, we live streamed it. So if anybody was watching this video and wanted to make their own, they certainly could, using the same technique that we just did. Yeah. Yes, I sell something very close to this as a product. Mine is actually way more involved in that. Like, that's the circuit. on my circuit board. Right? There's a
Yeah.
lot more going on there than what we just laid out.
Definitely. It's a lot more flexible, a lot more powerful than mine
Yeah.
is for a specific headset.
Exactly.
For a specific use case.
Which is why I'm not worried about you taking business away from me, because I'm not targeting I want to make a thing that is exactly from this to this, right? Yep. That is perfect for the DIY market. And that's why I'm encouraging you to do it. I'm encouraging you to take it to your club. I think DIY is a very good selling point of OHIS, right? Because it can be very simple. It makes a great DIY club project. Right. I think that's a fantastic selling point for it. And then there will always be people who are just like, I don't want to fuss with it. Let me throw money at the problem. Let me click the buttons, and a few days later, a magic box shows up that somebody else already designed. That's the niche that I'm filling.
Exactly.
So
now let me ask you a question on this.
Yeah.
So when you start selling the User Pro and the Radio Pro, will there be the option for somebody to order it configured for a thing, or are you going to sell it with the instructions on how to attach the cable for and configured for the thing?
So both. The way I'm doing it with EAP is that I made a panel of 4 of these in fabrication, and in each one of the 4 has a different configuration. So the 4 pre-configured User Pros you can order work with a Heil headset with dynamic, a Heil headset with an electret if you've got an IC element in it,
right?
A Radio Sport headset, and a CTIA PC gaming headset.
Yeah.
Those are, I think, going to be the 4 most common headset types. And so I have ordered the boards pre-configured for that. But pre-configured just means I've got 0 ohm resistors across the solder blobs. If you have a different kind of headset, you can buy any one of those and remove some resistors and put some solder blobs in other places and reconfigure it for your type of headset.
Right.
Pretty much the only thing that you can't reconfigure is that all the sockets are 3.5 millimeter. So if you've got a headset with a different kind of connector than a 3.5 millimeter, you're going to need to adapt that in some way. I may make other versions of User Pro with different sockets on it, but right now 3.5 millimeter is covering pretty much all of my use cases. So you can buy one that is pre-configured for those 4 types of headsets. Now, pre-configured doesn't mean you're done, because there's actually going to be a 2 LED VU meter on here and a trim pot. And so you will put the headset on, adjust it to where you like the mic with your voice. I'm very loud, so my mic gain is going to be turned down compared to somebody else's voice who may be more soft-spoken, or with a microphone element that's not quite as sensitive, or whatever it is. You're still going to have to adjust the mic level on your User Pro so that it hits the standard. Your device does not have a VU meter on it, and in theory, I have designed, but it's not yet working, an inline box that's just OHIS inline, and it has the VU meter circuitry on it.
Nice.
And so the idea being that you could just plug this in line with your headset and then use it to measure your mic level and adjust it as necessary.
As a config setup box.
Yeah.
And you only need to leave it in line.
You don't need to leave it in line, correct. You plug it in line once, you talk it the way you normally talk, you adjust the mic gain on your particular microphone. That's actually something we didn't add to your circuit. We might want to add that.
I was just thinking about that. We don't have a way to adjust.
Okay, we're done with this stream. We're way long on the stream. When we come back and rework your RJ45, we'll add that to it.
I think we've exceeded the Tam Radio Workbench record.
Oh no, not even close. We started at, well, we're pretty close. It's okay.
We're
3 hours. Yeah, that's probably pretty close. Yeah, so it's pretty close. The other thing that my tester does is it exposes it on a BNC so that you can connect it, the microphone audio, to an O-scope.
Nice.
Exactly. So there's an op amp on here that buffers it so that you're not actually going to impact the microphone by looking at it.
Right.
But you can look it up on a scope. So I designed this to be sold as a standalone product for people who want to make their own. So like if you go to your club and say, all right, we're going to get the club together and we're going to DIY 10 of our own design, right? You might buy one of these as a test tool to help you get all of your DIY ones set up.
Yeah, that's like I've got one of the choke test boards that I plan on building and making it available on club nights if somebody wants to bring in some cores and check them.
Yeah. So yeah, exactly. So that's what I designed this for. I plugged it in once and the VU meter is a little wonky, so I haven't spent a lot of time on this, but that's actually why I put the VU meter on the User Pro, is so that it's always available there to make it easier for the users of the User
Nice.
Pro to adjust their mic. I don't remember what we were talking about.
Well, we had talked about a trimmer. We were talking about doing yourself versus, the...
Yeah.
And I guess then the other part of that question that I had asked was, so the Radio Pro, will those be available pre-configured as a turnkey thing as well, if somebody wants it?
That's what it was. We were talking about pre-configuring. So the Radio Pro I designed, so short answer is yes. The Radio Pro I designed so that all the configuration is on this carrier board.
Right.
Which allows me to make this very generic. This is the expensive board. Right. And so I can make a bunch of these and it is absolutely generic. And then these are relatively inexpensive to make. And I can make these with, 4 or 5 or 6 of these different designs of these with resistors in different places for the different configurations. And then when someone orders a User Pro, they can select which config board they get with it. And I'll just grab one out of the bin and add it to the box. And then the user can add it, or maybe I'll insert it into the case before I send it off, whatever.
That's good, because with that and with the pre-configurable User Pro, for somebody who wants turnkey, I'm just going to plug in a piece of Ethernet and go. They don't have to solder stuff.
They won't have to solder stuff, but there are still trim pots down here that need to be adjusted for your specific use, your specific situation. So there is still a little bit of adjustment that needs to be done, but it's not.
It's no different than adjusting the gain on your radio. I mean, everybody's voice is a little different. Everybody's mic is a little different.
Except that to adjust the gain on your radio, you typically don't need one of these. Yeah. So, but yeah, once you, because the OHIS standard is, or the level at the OHIS point is a standard level. You adjust your User Pro to your headset and your voice, and then the output of that is a standard. And then on the radio side, you adjust your the Radio Pro to be the gain level of your radio.
Right.
And typically the way that works is you use your stock radio mic, and you set the gain on the radio itself to whatever you want it to be for your stock mic. So you can still use the stock mic normally, right? And then you adjust the level in the Radio Pro so that the signal coming from the OHIS signal
matches what the stock mic level is.
Exactly. Matches the stock level mic. And so that is specific to the radio side levels. And then the user side is specific to the headset and the microphone side. So there should be no adjustment when you take your headset from radio to radio. Right? Because it's the adjustment that is specific to my microphone and to my voice stays with the microphone and the voice. And the adjustment that is specific to the radio stays with the radio.
So the piece coming down the Ethernet cable is the same no matter what.
That's the goal. Yeah.
Yep.
Assuming everything is adjusted correctly.
Yeah.
Yeah.
Cool.
That's it.
All right.
Are you not in Kansas anymore, Toto?
So far, everything is still here. I didn't hear the vertical come crashing across the roof, so I think we're okay.
You think we're okay, yeah.
I've got an end-fed half-wave hanging off a old AT&T tower about 2 miles from here. We'll see how well the bungee cords held up.
Oh my God.
I had a friend who, at least in his experience, and he taught me that instead of using like a pulley with a weight, because sometimes that will, the wind will pull it and then it'll just kind of like snap back and stresses the wire. If you use bungee cords on both ends, it gradually moves. We'll see. Yeah.
All right, brother. I'm going to get moving. Qualifying for Australian GP starts in an hour and a half.
Okay.
I'm looking at it's 8:30 now, and it starts at 10 p.m. Pacific time. So that's what, midnight your time? You going to stay up?
Yeah, I'll probably watch it in the morning.
That's what replay is for.
Exactly.
All right.
So awesome. Appreciate it.
I had a great time. Hopefully the viewers had a chance to learn a little bit about KiCAD and kind of watch the process go through. Do you have any final thoughts or questions or anything?
No, I think we're good, and we just have a little bit of massaging to do.
Yeah.
Later. But we're really close, and I'll fix the graphic, and can't wait to send these off and get boards back.
That's right. I'm excited for you, Paul.
Because I got in 6 weeks, I got a Radio Pro coming.
About weeks? That, yeah, about that. So cool. All right. 73s, everybody.
73. This has been fun.
Enjoy. I'm going to wait until I see his wave in the thing, and then I'm going to hit the stop stream because it's always weird. I don't want to hit stop stream before we're done. There we go. There's me waving.